Good morning, mathematicians. Here we are. The big day has arrived. We are underway to be doing 8 hours of math. Dear Lord, what have I brought upon myself?
About addiction.
What have I done? Busy today. Can we do it tomorrow? Yeah, maybe it was irresponsible of me to do such a thing when finals are still on. 'Cause you young impressionable kids are gonna get distracted by infinity categories when you should be studying. I'm getting an ad for my own stream. Yeah, should I turn off ads? I don't know. I have ads on for stream right now, but maybe that's greedy. I don't know. Maybe I should turn ads off. If you guys yell at me enough, I might go do it. Yeah, I'm an evil man. I'm an evil man like that. Okay, let's copy this link. Let's copy this link and put it here. Our good friend of the channel, Nikolai, told me that posting links in the main post is de-incentivized on X because they don't want you to take it away, take people away from the site. You'll be studying alongside and listening periodically. Awesome. Thanks. Well, thanks for checking in. Is there a fundraiser button available for you guys? Let me see. Okay, it does say fundraiser underneath. Of course I like my own tweets. I like my own videos too. Yeah. I don't care. I'm not afraid to admit it. No, I don't think it auto likes. The charity, I think it's linked in the description. We'll go there in a second, but let me open up the book that we'll be using today. Marcus Land, Introduction to Infinity Categories. Amen, brother. Boom. Yeah, let's just jump right in. But yeah, let's go check out the charity. I think. Good morning, Mom. Mom, I don't know. Did I tell you this actually? I'm streaming for 8 hours straight today, and it's a charity fundraiser. Yeah. So here's the donate buttons here. So it's the Children's Hospital and Research Center Foundation. Yeah, maybe I should have edited that. I don't know. I didn't know what to put. Maybe I should have edited that. But anyways, can I not see? Should there be a? I thought there should be like a donation button or something that shows how much money we've raised so far. I guess I can check on that as we go. Yeah, I guess we can check on that as we go. Somehow I want to make it more obvious that we're trying to raise funds, though. Oh well. Kid sick at doing math. Yeah. Okay, let's delete this office hours and let's start a new sheet. Let's do the 8 hour stream. Title it as appropriately. Okay, boom, 8:01. I guess it's time to get started. Yeah. Dear Lord. Should add charity live stream to the title. Oh yeah, you're right. I should. Let's go. Boom. Let's edit this video. 8 hour infinity category. 8 hour charity live stream on Infinity Cats plus more. How about that? I'm not trying to tag anyone. How about that? 8-hour charity live stream and more. Boom. And add cut straight to Leo lectures. Well, I'll just verbally let you guys know. Y'all should go check out Leo lectures and support Leo lectures. Whoa, I didn't want to show you guys my dashboard. Am I allowed to post this on our math? I don't know. You guys can post it on our math. Does someone else want to post it on our math for me? It feels a little. I've posted stuff like this on our math before, but maybe if someone else does it, it's a little less like, I don't know, self-serving or something. Well then, yeah, Boris, would you do me the favor? Would you do me the favor? The honors. Okay. Yeah. Here's the best part of the book. Axiom. For every cardinal, we assume there exists an inaccessible cardinal above it. This is the best part of the book right here. Boom. More infinities than you could shake a stick at. Well, I think Boris will take care of it for us. What are K's? Oh, wait, did I spell something wrong? Hang on, did I spell something wrong? Thanks. I really wish I could see the donation button. Oh my gosh, I did misspell it.
Build a website you love.
Okay, let's edit. Have I published my work in a journal? My undergrad research is published in a journal. I have 2 preprints on Archive, but they're not published yet. Yeah, working on it. Growth in Deak universes don't exist. You don't exist. Boom. You don't exist. Okay. Let's dive in. Let us dive in. So, okay, to start off, review basic stuff of categories, yada, yada, yada. We all know this. Since you're a strict ultra-finitist, what is this inaccessible cardinal you speak of? 10 to the 100 is inaccessible to you. Well, fair enough. Actually, I don't even think, technically, if you're an ultra-finitist, thanks, Arad. If you're an ultra-finitist, then I think all the finite cardinals are still accessible, strictly speaking. But the natural numbers would be the smallest inaccessible cardinal. Well, a lot of people do research in undergrad, actually. Yeah, there's a lot of research projects that are accessible to undergrads, and it wasn't, my slice of the pie wasn't that challenging, but I wasn't doing like this stuff, I wasn't doing like crazy Langland stuff. I was doing graph theory things, which, okay, graph theory can also be very difficult, but this problem was not. You've actually done math where 10 to the 100 would be basically an inaccessible cardinal. What does that mean? Computer science? Right. So here's an important thing. We've got our category, full category of posets, the face maps. Yeah, maybe we should write this down because I'm gonna need this. I'm gonna need this for some rigorous computation. I know there's a particular exercise I want to do later. That's coming up. Hello, Adib Dolahi. Sorry about that. Finally got to stream early. Now you cannot understand what I'm talking about for more than just 10 minutes. Yeah, well, it's an 8-hour stream today, so you cannot understand what I'm talking about for 8 hours, actually. And I can not understand what I'm talking about for 8 hours. Okay, let's see here. How do I make this thing go away? I guess I don't. Right, so DI, of course, we have our usual face and degeneracy maps because we are degenerates. So DI is characterized by the fact that I is not in the image of DI and that it's injective. And then, of course, our favorite, since we're all degenerates here, is the map down to here, the degeneracy maps, which are uniquely determined by this property, and that SI is surjective. So SI plus 1 is this. Boom. Shout out to the professor who told you, I don't know why these undergrads do these random combinatorics projects. It'd be much more useful to learn something. Wow. Well, hey, I mean, learning atal cohomology is cool. But you're a computer scientist, yeah. Well, you could always yap about atal cohomology on stream on YouTube. Hey, maybe we could do a thing where we talk about atal cohomology again, and you just I mean, I know some of the basics, but maybe we could do some computations together or something. Don't approach the guy in the black van, even if he offers you atal cohomology. Yeah, if the van is white, it's good. Are there any infinite series for which we don't know the convergence divergence status of? Oh, interesting question. But a rod, does the Collatz problem really count? Because I mean, technically, I mean, I think this person wants to know in terms of like, you know, just an ordinary series, like a sum. That I don't know. And there's certainly series that we don't know if they're irrational or not. I would be surprised if the answer was no. Like I think we should be one. I believe that one should be able to cook up a series, right? Because probably if you think about things like questions about computability and whatnot, Collatz is a sequence. That's true. Collatz is a sequence, actually. That's true. Wait, but is it a sequence? Yeah, I guess you start at every number, but it never converges, right? Because it goes 4 2 1 4 2 1 4 2 1 4 2 1 4 2 1 4 2 1 conjecturally. Right. Oh, so yeah, I mean, we don't know. Right. I guess we don't know. Right. Okay. So I guess strictly speaking, we don't know if it converges because there could be other things that it feeds into, and those may not be loops. Yeah. Okay. There's a YouTube video on non-constructive proofs, Leo. Why are you giving us non-constructive proofs here? Adib is just fine. Okay, I'll try to remember just to say Adib. Okay, so right, this is our category of functors. It's a category of presheaves. And we've got the Yoneda embedding. Are we using a little Y for Yoneda? Maybe not here. You can always do something dumb like AN where N is 1 if hard conjecture is true and 0 false. Yeah, exactly. Yeah, and actually to that point, there's these extremely silly videos where Wildberger claims to solve famous open problems like the Riemann hypothesis or the twin prime conjecture or something, where he's like, he sets up some series, and then he's like, oh well, the series like if the series if there's finitely many, then the series is finite, and then and it's less than one, or if there's infinitely many, then the series is equal to one or something. Which doesn't, his setup of the problem is totally fine, but then he claims that that somehow solves it just by stating it in a different way, which is just completely false. But yeah, you could use that exact same idea. Think of sequence as of cycles. I don't know. You're a total noob at infinity category stuff. Are you alone? I don't think you're alone. I don't think you're alone. I wouldn't say I'm a total noob, but there's probably a lot of people here who are not experts. Okay. Got too much. Gotta reduce the red screen of my computer. What is the stream delay? I don't know. Automatic. Whatever the automatic stream delay. We're doing a short stream today. 30 seconds? Is it really that bad? I have no idea. This is Marcus Land's Infinity Categories. Introduction to Infinity Categories or something. Okay. A simplicial set is just a presheaf on delta. Yeah. Any simplex is called degenerate if there exists a surjection for m not equal to n, and any n simplex such that y such that x is equal to this. Wait, did we even define these pullback maps yet? One page in, I'm already lost. An n simplex is called degenerate if there exists a surjection, and an n simplex y such that x. Oh, an n simplex x. Oh, I see. Okay. Right. So x in xn is degenerate. If there's a surjection here for n not equal to m, and an n simplex y such that x is equal to alpha star y. Did we define what alpha star is? Did we define the pullback here? Delay is at least 15. Damn, that sounds bad. You put it on Reddit, but you can't post the link. Assuming mods approve it, it should be up soon. Okay, awesome. Thank you. Hello, head empty set. Oh, Luna. Oh. I was just the other day, or sorry, last night actually, I was looking back. I was like, how far have I come with my live streaming? And then I was looking back at, some like of the first videos. And I don't know. I don't know if you were there in the very first videos, but I was thinking, I was like, yeah, there's some people I haven't seen for a while, including Luna. So welcome. Glad you're joining us. You meant the colats as a sequence of number cycles? I'm still not sure I understand. A sequence of cycles, maybe? Your body is ready for the 8 hours? I don't know. Oh, alpha star is just the induced map on presheaves by composition. Right. Okay, so alpha star is like what I would also call hom. I mean x goes from delta op into set, and so alpha star you mean is like x at alpha, right? Is that what you mean? Your sleep schedule has been such that you're sleeping during my live streams. Well, happy you're able to make it to this one. Hello, the majestic lion. Hello, Tony. Hello, Tony. Welcome. Speaking of people I haven't seen on stream for a while. Simplicial set. Okay. Yeah. And n simplex is called non-degenerate. It is not degenerate. Thanks. We denote the category p delta of simplicial sets, S set. Yeah. Okay. And delta n is going to be oh, Ken coming in clutch. First donation of the morning. Thank you, Ken. Thank you, Ken. Children's Hospital, and thanks on behalf of Children's Hospital and Research Center. So, one thing I'm worried about in this 8-hour stream is losing my voice. What happens if around hour 4 I lose my voice? Do I just like put on some Chopin in the background and work quietly on stream? That'll be boring, I guess, but we may just have to do it. But let's hope that doesn't happen. I'll try and speak more from my diaphragm. So this is the simplicial set represented by this. Oh no, contravariant. And we will use the notation. We'll use the notation delta n sub m to be hom mn. You can also donate to Leo Lectures at leolectures.leolectures.org, right? Hot take, but Chopin is booty cheeks Bach or nothing. Yeah, I don't know what you're talking about, boy. You're gonna, you know what? No, I was about to give you a 1-minute ban, but actually, it's okay because I do really like Bach, but I feel like Chopin is my favorite. I think Chopin really is my favorite. I'll be honest. ASMR whispering about category theory for the remaining 4 hours. It may come to that. I don't know. What would that speed run look like, though? It would be a speed run of me trying to explain everything? I don't know. Okay, simplicial set, we look at the equivalence relation on the zero simplices, which is generated by relating x and y if there exists a one simplex such that the relation is reflexive, but in general neither transitive nor symmetric. Okay. The Elgar cello one? Huh? Elgar cello one? I mean, Bach cello suite preludes does go hard. What could possibly go harder than that? What could possibly go harder than that? Not much, I tell you. Okay, the Yoneda lemma. Yeah, okay, Yoneda lemma. Yeah, we got it. Double double Hom isomorphic to original functor. Yeah. And the Yoneda embed is fully faithful. The Yoneda embedding is fully faithful. Classic. So then corollary, there exists a canonical bijection here. And why is that? That's just Yoneda, I guess, but I should write it out. Speedrunning from kindergarten to math research is pretty much what mathematicians do. Yeah, I mean, kind of. Yeah. One of the only things on your bucket list is to listen to Mahler 5 live. That sounds great. Wow. Thank you, Anonymous. Thank you, Anonymous. $20. We've raised, I think, a total of 25 already. Less than 25 minutes in, and we've raised $25 for the kids. Fantastic. Yeah. Bach Andante is your favorite Bach? You don't care much for piano? You know I just bought a piano, right? You know I just bought a piano. Right. So hang on. Yoneda embedding is fully faithful. Yeah, Yoneda says... Yoneda didn't say... Yoneda says, touch your nose. Hum, boom, boom. I just got I don't remember, Yamaha P something. You expected math people to move more into jazz and classical. I suspect that there's correlations between the areas that people are into. I mean, I do like jazz. I really like math rock. I really like, weird time signatures, and I definitely want to learn more about like jazz chord theory and stuff for sure. But yeah, right now, I've been working on some Chopin, some Satie, and some Radiohead. Yeah. For non-representable categories, what's a representable category? You think math rock is kind of lame? Okay, that's it. That is it. That is it, Leo. We were doing, boom, 1 minute timeout. 1 minute timeout for saying math rock is lame. Boom. First 50 USD donation goal will be playing piano. Maybe. I mean, it might be difficult to move my setup over to the piano, but it may happen at some point today. And we've got 8 hours to kill here. Did jazz from 14 to 24 and math from 24 to now. Well, what is now, Ken? What is now? Right. So why is this true? So if we plug in n's everywhere, right. If we plug in n everywhere, wait, what goes here? This is x. So we plug in n for x. Right. And then of course this is literally delta n. Yeah, so direct consequence of Yoneda. You're 29, started math in 2020, second year PhD student now. Hell yeah. Yeah, man, if you think Ken is old, I am deceased. Okay. 29 is not old, no, but 30 is. There's two kinds of people in this world. Young people being underneath 30 and old people being 30 and above. That's it. Everyone under 30 is in the same boat. Everyone over 30 is in the same boat. That's how the world is. I don't make the rules. I just report them to you guys. Tony, bringing us to Let's see if I can do basic arithmetic and keep track. Up to $30. Thank you so much, Tony. Five euros. So that's coming in. That's like $1,000 Canadian. So really coming in clutch. Hom takes 3 inputs. Yeah. Well, we're applying Hom twice. Wait, first dash is a typo. Oh yeah. Oh yeah. Sorry. This should be a Hom between these two functors. Yeah. Sorry about that. What is this? A Hom of a Hom? Well, it's Hom. It's Hom between functors. It's Hom between functors. But yeah, I mean, maybe you could keep taking Homs and take a limit of that or something. It just turned 20. Feel ancient. Is it snowing in Canada? Let me show you guys. Maybe later, if we do a walk around my apartment or something, I can show you a snowier view. But this is the view out my bedroom window. Doesn't look that snowy, but could be snowier from the other views. Maybe there's some way I can attach my phone to stream. Then make it easier for me to like go for a walk, or like at some point I might have to make food for myself. So I don't know what I'm gonna do. Bring you guys to the kitchen with me. Yeah, learning diff geo. Hell yeah. You are Abraham from Egypt. Welcome, Abraham. You're a math student at your first year. Any advice? Yes. Really learn the fundamentals very, very well. Make sure you really understand the fundamentals. Of course, spend some time to be creative. Spend some time to read ahead to books that are more complicated than you can handle at the moment. Like in this live stream, have some fun. But as tempting as it is to jump on to the fancy stuff, really drive home those fundamentals. You can't donate because of where you live. Yeah, this has happened before. So I would just ask, if that's the case, then just donate to some like local children's hospital where you can live. I'll just deviomorphic listen. I don't know. Promise me you'll send them whatever. Maybe there's like an online place you can donate for a local thing. So just do that, and we'll still be helping people. We got colimits. We love our colimits. We'll probably... I mean, my understanding is the whole point is that, of this infinity category stuff is that we want to be able to take... No, this is not for the hospital in Calgary, Mom. Because unfortunately... So, I would have done Manitoba Children's Hospital. But... when you're signing up for charities, like on YouTube to donate, there's only like pre-selected places that are like officially registered charities or something. I think they're pretty much all in the States, although some may be international organizations. So so anyways, yeah, it's a children's hospital and research center in the States. But since they're doing research, I feel like this is something that technically does help everyone in the world. So whatever. Yeah, Leo Lectures does some great videos. Have I been to Regina? Yes, unfortunately. Is it nice? There's a summer school in Homotobi Colimits. I want to go. Oh, yeah. I don't know. There's a friend of mine who said he actually really liked the actual city of Regina. Yeah, I mean it's we like to make fun of Saskatchewan, which is the province that it's in. But yeah, I don't know. I would say go. I would say go. Yeah. Actually, if there's a whole summer school in Hometobi colimits, I maybe I'll go. Maybe I'll go. I'm thinking about taking time to go. This is Marcus Land's book. This is about Marcus Land's book. I'm uh, taking time to go stay in Winnipeg for a bit, um, between the end of my degree and the start of postdocs. So yeah, maybe I'll sign up. This is like right next door, by which I mean like a 9 hour drive or something, but basically like right next door, by Canadian standards. So um, yeah, okay, cool, cool. Speaking of hospitals, is it a thing that a lot of mathematicians were ill during childhood? I've never heard of that being a thing. I was saying the point of infinite. Well, oh, the point. The thing that I understand. Well, I mean, there's several reasons, but one thing that makes infinity categories nice is that you can take limits in a way that, for derived categories you can't. Or just like limits of triangulated categories more generally aren't so well behaved. And for you can do like you can build like an infinity category version of a derived category. And one of the things that I'm interested in is, for example, there's like these stacks of like, um, there's some stack Y, which is going to be a stack of Langland's parameters, which is all in the fancy version of my research. And the way that you define, what the derived category of quasi-coherent sheaves should be on that stack is a limit over all the like affine schemes, except actually this is like in a derived sense because everything has to be derived, blah 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 blah. Hello, Fimno. But yeah, the point, one of the motivations, I guess, for me, because I eventually want to understand things like the stack of Langland's parameters, and quasi coherent sheaves. You're right, Leo. I'm not that well behaved. Is exactly this idea. When was the last time my mom was able to help me with my homework? Well, yeah, not for a very long time. In fact, my mom is a my mom. Well, she's retired now, but she spent a long time as a school teacher, and she still tutors on the side. And sometimes I uh, help her to help the students. Um, yeah. One of the axioms you clicked on. Oh, yeah. Talk on Zermelo, AC, and wheel ordering. Nice. Yeah. This definition of QCO can actually be phrased as a right-con extension, which is arguably more fundamental than limits. Nice. Yeah, I mean, maybe later on in the stream we'll end up reading more about that, somewhere. Maybe we'll go look at some QCO stuff. I don't know. Depends on how far we get. Obviously, I get very distracted by yapping here. So, one can phrase general colimits via, oh yeah, initial. Do, do, do. Oh, maybe we should read this. Sounds important. We can phrase colimits via initial and terminal objects, right? Because it's a terminal object in some like arrow category. Point of view will be important for infinity categories. Given a functor, we consider the category of cocones of this functor. Given a category I, we consider two new categories, which are constructed from I by adding an initial, respectively terminal object. There's an obvious functor here. We can thus consider the functor categories, which is strict to F along the above mentioned inclusion. They are called the categories of cones and cocones over F. Right. Grateful. Mom is grateful for my help. Math is definitely not your area of strength. Yeah. Well, you're welcome. This definition. Oh yeah. Next video, math PhD student roast middle school arithmetic homework. Yeah. I never understand this comment that Defiomorphic has dropped several times. G Mozzie, donating. Thank you so much. Thank you so much, G Mozzie. What are we at now? $35? I can't even keep track. Thank you so much. We're raising good. We're I think we're keeping pace roughly with $1 a minute, so that's crazy. NLab on carrying. Right. Yes. There's a whole nice paper that there's a nice little article that talks about carrying as group cohomology. Be nice to make a paper on that one day. I don't know. Cocone has a nice sound to it, though. Following lemma follows immediately from the definition of colimits and the fact established in exercise 6. We didn't do that. That the category set is bi-complete. Otherwise, the statement does not make sense. So what does this say? Right. It says that we can flip limits out. And maybe I should write this down because Lord knows I will forget which direction. Nah, we'll come back to it when I need it. Hope everyone is having a wonderful mathematical December. Hope you are too, G Mozzie. Hope you are too. It's rare to see fancy math with good formatting. I don't know if I agree with that statement. Right, we got adjunctions. Adjunctions preserve limits. I will also get confused about what side goes where. Left adjoints preserve. Yeah. Left is co. Yeah, I'll never remember this. And you can't make me. Okay. Let F be a functor which admits right adjoints. Then there's a specified right. Yeah, uniqueness of adjoints. Yeah. And even by a special guy makes them isomorphic. A category is co-complete if it admits colimits indexed over arbitrary small categories. And it is bi-complete if it is both complete and co-complete. Yeah. If C is bi-complete, then the colimit is left-right adjoint to the diagram functor. Yeah, I think I said some stuff. In my sheaf series about this. Of course, I've forgotten. Okay, maybe we should look somewhat carefully at this proof. RAPL. Right. Okay. Right adjoint. Wait. PL. Wait. Right. No. What is RAPL? It's the title of a book chapter in Avodi's book. So it's burned into your brain. Real also uses this abbreviation. Wait, how does it work? Right adjoint purple limits? I don't know. My brain's not working. It rarely does. Is there a relation between co-complete to existence of zero objects? Could be. Right adjoints preserve limits. RAPL. Right adjoints preserve limits. Okay. Nice. Okay. If C is bi-complete, then the colimit is left-right adjoint to the constant diagram functor. In particular, the following colimits wait, forming colimits determines a functor. Right. So fun IC to C by taking colim is a functor. And in particular, it's adjoint to constant. Yeah, I think I went through this in my sheaf series, so I'm gonna skip it at my own risk. Yeah. And left adjoint is right exact. That one I can remember because it's like opposites. You're supposed to do algebraic topology now, but you keep getting distracted by more and more category theory. Yeah, well, I mean, eventually they just kind of become the same thing, right? Right exact is quotient preserving, hence preserves colimits. Right. Okay. Yeah, limits are like subspaces of products, and and left exact is like preserves injections, whatever. Have you ever looked into topological quantum field theory? Not in any depth. To be honest. If you're complete and co-complete, you must have terminal and initial objects. But not necessarily zero. Okay. If we have an adjunction being left adjoint to this, then the functors here F star is given by post-composition with F, and likewise G star is post-composition with G. I see. Again, form an adjoint pair. Good to know. So this is the dangerous part. I'm like starting to get bored of these like basic propositions here, but we probably really need this for future sections. Okay, this is probably a important corollary, is that the category of simplicial sets is bicomplete. Okay. So we're just saying this functor category is bicomplete. A colimit over this diagram is given by the functor ascending I to there. Okay. Leo Lectures does have the humor, indeed. Does have the humor, indeed. Yeah. Okay. What do we got here? What's this definition? What are we defining here? Oh yeah, the slice category. D is a category, X is an object. The slice category is pairs of things living over X, right? And there's a canonical functor. I've got a functor here. Define the slice category. If F is a functor and X is an object, we define the slice category associated to F and X by the pullback here, right? Thus, I better write this down because I'm going to get it twisted later. Fx has objects, so F is a functor from C to D, and this has objects given by things in C together with morphisms from F at C to X. Wait, sorry, these are objects. Right, and then morphisms make an obvious commuting triangle. Let's see. Right, so a morphism will be C, C prime, F beta. I forgot to mute group chat. Terrible. How do I mute it longer, though? Editor permission so that you can run polls in chat. Oh, how do I do that? How do I do that? Remove as managing moderator. Can I remove you and reassign you? Add as moderator. There's only two, just standard and managing. So I'll put you as managing. What if someone in my group chat made a new discovery? What if? I mean, there's people that I think research level people that have shown up in chat. I mean, just we had a guitar freak showing us there. We looked at one of his papers, so yeah. Okay. Well, I don't know. I don't know if I'm gonna bother. I don't know if I'm gonna bother editing that, changing that now. Yeah, I don't want to go spend a bunch of time fiddling with the settings now. Sometimes someone in your group chat discovered that they took one of their muffins yesterday. Oh, that you took one of their muffins. Well, you should get booted out of the group chat then. That's sacred stuff there. When f is the inclusion of a subcategory, sometimes in particular when f is the inclusion of a subcategory, we simply write cx over that, right? Oh, wait a second. There's another. Yeah, no, that's all I need. There's a dual notion built from this. I like this. Wouldn't it make more sense to have this notation though, right? X over D. I mean, that would make sense to me to use that notation instead, but whatever. Okay, here's an important lemma, I think. Every presheaf is a colimit of representables. More precisely, for every presheaf, the tautological map is an isomorphism. Okay, so now we need to build this tautological map, which relies on Yoneda. So we need to show that this map induces a bijection on an auxiliary presheaf. So let's see. Right. So we're plugging in. Right. We're seeing what we get out when we hom into here. Right. This is like your space is the gluing of spaces mapping into it. Right. So we plug it in here, and then we know that we can pull a colimit out in front, and it swaps to a limit. Right. And then what is this? I mean, I guess this is an application of Yoneda to get GX. So it's not hard to see that the latter is in fact the set of natural transformations from F to G. This thing. Yeah. So let's see. Why is that the case? So X in C over F. Wait, C over F was what now? C over F is what? What is C over F? Wait, did we define that notation? We have C over X. We have F over X. We have D over X. C over X, F over X. What is C over F? Oh, because that's in right, because it's Yoneda. Yeah. So, wait. So C X is in C over F. Comma, category. Right. So C over F. Yeah, nice, Leo. We probably, due to the delay, I think we delivered that joke at the exact same time. So, right, X should really be thought of as, I mean, we should be thinking about F. F is a functor. F is an object of the functor category. So, I mean, really, this should be like PC, right? And then, so X is an object that is a functor mapping into F, right? And then what does this mean? G at X? Now I'm so confused. Sees the word comma, I don't know what to do. Yeah. No, I mean this really should be an object of C. This really should be an object of C. What is C over F though? This notation's not defined. This notation isn't defined. Maybe it's a typo? The objects would be pairs. Pairs, you mean triples? CSF, where C is in C, S is a set, and F goes from S to F at C. Right. So, right. Okay. So then X is really going into, right. So we have the choice of so this is a set S together with a map into Fx. A notepad to write the errata. Well, it's probably me that's made the mistake. But then we're applying G to those objects. And then how's this limit defined? Morphisms X to F are exactly how F are exactly Fx. If X is in C. Okay, let's just go to comma category. Is this too general for what I want? Slice, co-slice. Okay, hang on. Let's just go back to the document for a second. There's a colimit over all x in CF. Colimit over all x in C over F. So the colimit should be over the diagram you get when the x's are over F. Right. Think of manifolds as sheaves of Rn. Lying over F. Right, so we should have IC. So it should be like hom x, and then I guess the arrow goes the other way because of like contravariance. So the category should look like this, right? You'd love me, but I'm far away and we're not friends. Damn. Yeah. Well, who knows? Maybe when I move, we'll be closer and then we'll become friends. Who knows? Who knows? You could always do that. Always nothing like some what's it called? Parasocial relationships. We could get parasocial up in here. But you cut off the arrows to F. I cut off the arrows to F. Yeah. I don't know what this means. I don't know what this means. Right, I mean, we hom, I guess. Yeah, I guess I don't really get it. If you don't cut off the arrows to F, the colimit is trivially F. I see. Right, but then why are we even saying the colimit of X over this thing? Because I guess we're only considering those arrows between these that make this diagram commute. I guess we're only considering the arrows here that allow these diagrams to commute, I suppose. Okay. So this last thing then, what do we have? I mean, it's the limit over x in CF of gx. Right, but we need to remember, we do need to remember that we had this arrow. So it's the object's gx. It's the object's gx, but it's not hard to see that the latter is in fact the set of natural transformations from F to G. From F to G? From F to G? Fun fact you learned in this lecture by Gates-Gorey when he was defining Zariski topology for an arbitrary pre-stack. Wait, what did you learn? Oh, the thing about about cutting off the arrows. Why? We have G. The lemma I'm doing now, yeah. Okay, but how do I interpret things in here? How do I interpret things here as a natural transformation? Okay, I'm starting to, because there's some commuting of a diagram here, I'm starting to, okay, I can kind of see it. I can kind of see the outline in my head. I can see it. This should be a compatible family of maps, right? But why taking the limit? I don't know. What's happening? We're spending 8 hours on infinity categories and maybe other stuff. The funny thing is, I've looked at this exact proof in this book before. I think I even printed out some pages, and I convinced myself that it was true, and I don't know why I'm struggling this morning. Yeah. The set of natural transfers from F to G. From F to G. From F to G. It's just unrolling definitions, yet somehow very hard. Yeah. Yeah. I mean, the limit is what? I mean, the limit should be some universal object where we have arrows from here. Oh, I see. Right, because this should be like compatible with all arrows. So like if F goes from X to Y, then we should have a map going in the opposite direction here, right? We should have this. And now these things all, right? But then these things have diagrams into F. Right? Something like this. Something like this. So I'm starting to see it. Right? This is a set of why is lim itself the set of natural transformations? Yeah, I don't know. I'm about ready to move on. We spent a lot of time on this. I'm just gonna check in on stream. See, I want to know how many people are tuned in still. We're past hour number 1. We're 1/8 of the way through. Wow, 32 watching. Wow, it is bumping in here. I believe I have things slightly backwards. That is possible. Wait, I want F to G. I do want F to G. This is a limit of sets. Oh, right. Hang on. Okay. This is a limit of sets. Right. So this should be some collection of a product, some subcollection. This is like a product over all, X in CF of. I mean, it's this what subject? It's a subspace of this subject to some compatibility conditions. Well, I mean, F to. This is our data, yeah? Subject to some, so what is, so maybe put a prime here. So what is an element of this thing? Well, it is a collection. So an element of this, eta, an element of this is, God damn it. I mean, an element of this is a choice, but now this seems weird because it's a choice of eta in GX. But I guess maybe Yoneda, we can Yoneda something. So it's an element of GX for every X. But by Yoneda, that is a natural transformation, right? But by Yoneda, that is a natural transformation. Right? Where are we here? I'm regressing in the document. We're going back in time forever. Yoneda embedding is fully faithful. Yeah, where's the... So, by Yoneda, that is Hom. That is Hom from Hom into here into G, right? It's not only indexed by X, but it's also the data of X into F. Well, isn't it? Wait, in this case, it's into G. Just direct logic of being presheaves valued in sets would be fine. But see, I'm so confused. Just doing it directly, it says that eta sub x is an element of gx. Why is it a morphism of f into g? Why is it a morphism of f into g? I mean, I guess it's in the over category. So, I mean, there's this, and then there's also a map from here into F. C over F is also called the category of elements of F. So for each C and each element, it picks out an element of GC. This is because of what a morphism of F into G is. You give X over F, arrow an element of GX. Eta X over F. I'm so confused. Yeah, I'm still confused. For every x, we have, I don't know, I'll call this an eta over x. We have an element of gx. And we have an arrow from this Hom into f, right? I mean, you're right. Now my logic would treat every manifold as having a point. Yeah. Your manifolds comment isn't it's not eta p, it's eta of the point to the manifold. But hang on. I mean, strictly set theoretically, this is a limit over gx. The gx are sets, right? So an element of this product is a choice for each, for each x over here, for each map into f here, call it alpha x, I don't know. For each choice of map here, we're getting an element of gx, right? So for each map, an element of gx, of which x to f which is example x to f, which is f at x. Which is x to f. Wait, what? Yeah. No, I don't get it. I just don't get it. I just don't get it. I don't know what to tell you. We're skipping it. We're moving on. We spent too much time on this, and I don't understand. We're moving on. Even though this is probably a very important point, which I have... I used to think I understood it at one point. Clearly, I don't. Clearly, I don't. Okay, wait a second. One more thing. Can I go from the backwards data? What if I had a natural transformation? What if I had a natural transformation between each of these things? No, I don't understand. The problem here is understanding C over F. Since the subset of that product is directly semantically the data of what a natural transformation is. They didn't define C over F in the book. No. They did not. But even so, right? Am I like gx is a set. G at x is a set. And so an element eta of this product is going to be a choice of element, is going to be a choice for each object x. It's going to be a choice of element in gx, right? The actual hard part of this is when you don't have your super infinity axiom and you have to argue that the product exists in the first place. I'm not going to do that. Yeah. Anyways, let's move on. Let I be the small subcategory and D a bicomplete category. Here are some other important definitions. So we have I from C naught into C. I guess we'll write subset. Doesn't matter. Doesn't matter really. And F goes from C to D. Then the restriction functor from the functor category C to D to here has a left adjoint. So we get adjunctions here. These are our favorite adjunctions. These are our favorite adjunctions. And they're given as I shriek of f evaluated at an x is the colimit over c in c naught over x of f of c, and the other one is the limit. Y is the limit of y in here. Wait, is this a typo? Oh, and there's a difference between, there's over and under here. Here x is over the slash. Got to be careful there. X is over the slash. Maybe this is a typo, because certainly this should be f at c, right? That should certainly be f at c. You would think category theory books would really emphasize and go through proofs of really important results like this in detail. Well, they do, but I mean, this is, you know, technically everything in this section is just prerequisite material. And probably you could find more detailed proofs of these statements in, say, Reel's book, or what's the other one? The one that I like and always recommend and can't think of right now, Tom Leinster. Certainly, these are statements are probably covered in detail there. But what am I saying? Yeah, this is all background, but we haven't even started the actual textbook yet, really. It's almost like the more important a result is, the more they want to do the proofs as cleanly as possible. Well, it's good to know how to do clean proofs, though, right? I mean, that's why we like this technology, because it gives us clean proofs. You don't think you would understand it without various space examples? Fair. Yeah. Skip the prereqs? Maybe. Glad you found this stream. Just started going through category theory and context. Nice. Do I ever find myself thinking about foundational set theoretic issues in category theory? Yeah, like 2 years ago I had an existential crisis. Or no, a year ago? Yeah, maybe 2 years ago I had like an existential crisis about large cardinal axioms. But then I went and read up on them, and now I feel fine accepting a growth in DQ universe. And I have a little video. About it. So maybe I should remind the viewers, now that we're almost an hour and a half into this. This is a charity fundraiser. So please, if you got anything to spare for the Children's Hospital and Research Center, please feel free to donate. Yeah. And then you decided that growth in DQ universes don't exist? No, they do. They do. Any links to resources on that? Ooh. That's a good question, actually. I can't think about any particular resources at the moment, but oh damn, here we go. $20 coming in clutch. Tied for top contributor in this stream. Thank you very much. Thank you. Yeah, resources. Oh, Arad has dropped a resource here in chat. Yeah, I think honestly, I think I just Googled random PDFs, and that was how I learned for the most part. So, okay, con extensions. Right, those are called con extensions. Okay, maybe Arad's right. Should we skip some of the other No, we should look at this one. Well, we should at least write this one down. There's not even a proof, so. But this is important, right? I think we're going to use this. If X is a simplicial set, it is isomorphic to the colimit of all over all of these things. So this is super important. Easy way out? Well, what's the less easy way out? You've been finding your own way through those issues like univalent categories of hot. Nice. That's a cool way to do stuff. Yeah, like I know that somehow this is supposed to realize like if you have a simplicial complex. And I think in a moment he's going to state a topological theorem here. Like if you have a simplicial complex, then somehow your topological space should be like a colimit over each of the n simplices or something. I understand this on the level of vibes, but not on a level of rigor. Maybe we should look back to the comma category once more. Let me see how many viewers we got. 33. We picked up one. Almost like measure theory, you have to do bookkeeping to show that in your various examples things still exist and can be made out of sets. Yeah. But I mean, what else does... I mean, you still have to do bookkeeping, but... yeah, I don't know. I believe in growth in deep universes. That's all I'm saying. You got to. You don't have a choice. If you want to consider the category of groups, you need to believe in a growth in deep universe. I mean, you could say a proper class, right? But then, in my opinion, that's worse because you get the same thing at the end of the day, except now you're introducing a whole new kind of object that's like different from sets. So if you got to introduce some new bigger thing anyways, why not keep it sets? Yeah, okay, maybe we should try and understand this a little more. A, B, and C are categories. A pair of functors into C. The comma category, S, T. I'm going to try and understand this. Okay, I'm going to try and understand this. Maybe, should I skip? I don't know. What do you guys think? Should I skip all these prerequisites? S, T, S down arrow T is all triples. So maybe let me make these like math bold or something. So it's triples A, B, H, where H goes from SA to TB, and then morphisms are pairs, making that triangle that square commute. GU axioms? Oh, growth in deep universe axioms are extraordinarily strong. But they're not actually extraordinarily strong. Like if you talk to a set theorist who works with large cardinal axioms all the time, they're actually not very strong at all. The set theorists work with way stronger axioms like on a daily basis. And what else was I going to say? And also like the thing is you just kind of need them. Like does introducing proper classes, is that somehow less strong than growth in deep universes? Like you want to consider categories of sheaves on a space, and you want to consider categories of functors between those spaces, and probably at least one level up. So that's because that is what set theorists spend their life doing. Yeah, I guess, but I don't know. I think we should believe set theorists. That's my hot take for today. In hot, the underlying collection wouldn't be a set, but a groupoid, right? Because under univalence. Yeah. Really? So growth in deep universe is that much stronger than choosing a proper class? This is news to me. Okay, so if we take, right, the over category, yeah, so the over category is that co-slice category. An object. Where's notation that's like a category over a functor? Okay, you know, I'm just at this point I'm just skipping it. I'm skipping ahead. That's a hot take if you've ever seen one. Yeah. You don't need a growth unique universe to do morphisms between sheaves. Well, if you want to talk, you need, well, okay. You need a large cardinal if you want to talk about the category of sheaves, though. You need a large cardinal if you want to talk about the category of sheaves. And then you need an even bigger cardinal if you want to talk about functors between sheaves. So the category of functors between sheaves. In your mind, classes are more of a syntactic thing than a semantic thing. Saying X belongs to a class is like saying X satisfies the formula that defines the class. Good morning, Tenacity. Good to see you too. Thanks for stopping by. Although I guess I don't physically see you. No, you don't? What do you mean, no, you don't? The category of sheaves is bigger than any ZFC set. So you need a class or a bigger set. Like you're going beyond ZFC if you're talking about if you're going beyond, if you're talking about that category. I mean, okay. You could define, you could do something horrendous. Sheaves on literally anything, on a point. Sheaves on a point. Like you could do something horrendous. Sheaves of sets on some category. I mean, look, on a topological space, like the category of sheaves. Look, the category of one-dimensional vector spaces. The category of one-dimensional vector spaces over the field with two elements. This is literally bigger than any ZFC set. Yeah, I mean, sheaves on a point is just set, so. Let alone going to some bigger space. So okay. But let's skip through. Gosh, we shouldn't skip through this stuff though. I can't make up my damn mind. Why does one need inaccessible cardinals to talk about set? Because the objects, the collection of objects, right, of set, the collection of objects of set, this is not a set, right? This is too big to be a set. So either it's a class, in which case you're going beyond ZFC, or it's an inaccessible cardinal, in which case you're going beyond ZFC. You don't need your collections to be sets? I mean, well, they're either classes. I mean, this doesn't make a difference, though. Like, it's a class or it's inaccessible. Similarly, the collection of covers of a space is larger than a set. Yeah, exactly. I mean, this is exactly the whole reason why this textbook starts off. But you can't handle it within ZFC. You're beyond ZFC. The class of all ZFC sets is like that thing as an object is you can't construct it in ZFC. No, you can't define the class of all set. That's not in ZFC. The axioms of ZFC do not include classes. It does not include classes. The word class doesn't appear anywhere in the axioms of ZFC. That's the whole reason why in this book we start off, the very first thing we do in this book is add this axiom, right? In addition to the usual ZFC axioms, we'll assume the large cardinal axiom. Yes, you can talk about an object being a graph in ZFC. That's perfectly reasonable. That is a perfectly reasonable thing to do. But you cannot talk about the collection, the object, which is the collection of all graphs in ZFC. That is something you cannot do. You can define the class of all sets like that. It's part of the framework. But you can't do that. You cannot construct. That is not something that is constructible by the axioms of ZFC. You cannot form this set. You cannot form this set in ZFC or class. I mean, you can't even quantifying it over it or not. Like, this is not, like, you can't construct it in ZFC. And yes, I mean, in any case, we do want to quantify over the whole thing. The title of his book is something infinity categories by Marcus Land. You can't form the set, sure, but I mean, a class is not. But also, ZFC doesn't give you the words class don't appear in the basics of ZFC, right? ZFC is a collection of rules by which you construct sets. Right. And so, yes, or Rod, you're right. It's a class, but then we're going beyond ZFC if we're forming a class. Sure, I agree. You don't need to quantify over those. You can still talk about a sheaf, and you can still write down a morphism of sheaves in ZFC. I agree. I've zero disagreement with that. But if you want to consider the category of sheaves on a topological space, now you've gone beyond ZFC. Yeah, I just don't know if I agree with that, Arad, though. But like I just don't agree with that at all. Otherwise, what's the whole point of introduce like? Yeah, I don't agree with this point at all. The problem is that while we do have proper classes interpreted as formulas with one free variable, it's fundamentally a meta-theoretic notion. Yeah. You can work with a category of sheaves on topological space with ZFC, but it's you can't, because like what exists in ZFC? Things that you can construct from the axioms, right? What exists in ZFC? Things you can construct with the axioms. So what can we construct with the axioms? Well, the empty set, the set containing the empty set, the rational numbers, the real numbers. These are all things that we can construct in ZFC, right? And we can construct a topological space, and we can construct a sheaf on that topological space, right? But one thing that you cannot construct within ZFC is the collection of all sheaves on a topological space, because it's not a ZFC set. But of course models go beyond ZFC. You can still define models, yes, I agree, which are not sets, yes. And I agree you can't quantify overall models. That's not at all what I'm saying, Leo. I'm not saying that at all. I'm not saying that you can't work with things being a graph or not because the class of graph is not a set. I am not saying that at all. I am not saying that. And I agree we can define sheaves. I have no problem with this. We can define sheaves in ZFC. That is not at all a problematic notion. I'm also not good at these things, Adib, but and you can define data for natural transformations. Not if your category is large. Not if your category is large. Actually, wait a second. Even sheaves may be like you can define a sheaf. Actually, wait a second. I mean, if we're actually perhaps that's not even true, right? Because if a sheaf goes from, say, open X, I mean, if you're framing it as a map into as a functor between these categories, then actually you can't, because in order to build this category, you're going beyond ZFC, right? You can take a more naive definition, right? The sort of classic definition. You can call it an assignment from each open set. You can assign to each open set, say, an abelian group, and define the compatibility relations and everything. But actually, yeah, strictly speaking, no, you can't even define this, because you can't form the category of abelian groups in ZFC. You just can't construct it. Yeah. Hello, Sergio Polar Bear. No, you can't even define id set in ZFC. Because you can't define set. You can't define set in ZFC. In set theory, you're allowed to define functions from ordinals. Yes, I completely agree. You can define functions from ordinals because you can construct an ordinal, and you can, right, an ordinal is a set. A bigger ordinal is a set. A function between ordinals is a set. Perfectly fine. Perfectly fine thing to do. This function wouldn't be a set. Why wouldn't it be a set? I mean, it's just a subset of the Cartesian product. A function's just a subset of the Cartesian product. That's perfectly fine in ZFC. Define functions. Oh, sorry, from ordinals. You mean from all ordinals to sets? I don't think that's. I mean, everything in ZFC is a set. And so you have to be able to construct the set, right? And the set of ordinals, the set ord. Ord is not a set. You can't construct a collection of all ordinals within ZFC. One of the axioms one of the ZFC axioms is literally that the image of an assignment, when specialized to a set, is a set. Which axiom is that? Yeah, but ord is not a set. That's true. Set theoretic issues are not, and this is supposed to be infinity category live stream, but yeah. Which of these axioms are you talking about? Arad, or Leo, sorry. You can't have formulas exist in your objects you are quantifying over. I'm not sure what you mean by that. But why don't we ask Math Twitter? No, that's probably a bad idea. I'll turn into a cesspool. If you're asking for every object, including your assignment formulas, to be sets, you get a contradiction. You're studying for algebraic geometry final and then came back to a ZFC axiom talk. I just don't think. Okay, what if let's just Google it. Can you? I mean, what's the right way to phrase this question? Axiom schema of replacement. It says applying a class function to a set gives a set. This is not the axiom of replacement I learned. There's no mention of class whatsoever in the axiom schema of replacement. Let phi be any formula in language of ZSC whose free variables are among all of this, so that in particular B is not free in phi. The axiom schema of replacement asserts that the image of a set under any definable function will also fall inside a set. So that's... Thank you, Anonymous. Thank you, Anonymous, for the $20. Wow, we've got now three or four $20 champions donating here. Thank you so much. Yeah, phi is any formula, but you have to apply it to a set. You have to apply it to a set. And like the collection of all ordinals is not a set. Okay, so let me say this. There is a way, let me say this, by the way. There is a way to define the category, to define the category of all sheaves in ZFC. So for example, you know, the skeleton of the category of all finite dimensional real vector spaces exists, right? We can just define it to be all the RNs and stuff. And so you can use a similar strategy. You can use a similar strategy to define a category of all sheaves on a topological space. So technically, in that sense, you can use a similar sort of trick. But the problem is because then once, you know, we go to all these formulas of like, you know, defining like pullback of sheaves, now it becomes really messy because somehow you have to make it turn into this like essentially basis choosing formalism. And it's just an absolutely awful nightmare. Sorry. Okay. Yeah. Let me say this. It is okay. You can't form the way that we normally form the category of the category of finite dimensional vector spaces, right? In the way that we normally define it, by which we mean it's a set together, you know, it's some set together with you know, these operations that make an abelian group and a scalar product. This can't be constructed within ZFC. Why? Because you can do this on any set, right? You can form the free vector space, for example, on any set. And so this is just too big. It's just too big because if you forget to sets, like there's at least as many vector spaces as there are ZFC sets. You can't construct the collection of all ZFC sets in ZFC because then you get a set of all sets, right? What you could do is form something like the category whose objects, for example, are all RNs, right? You can't construct the set of all sets. That's what you can't construct. You also can't construct the class of all sets. Like, you can't treat the object, which is the class of all sets. That is not an object in ZFC. Right, but ZFC is just a theory about sets. Like, can you construct the class of all sets within ZFC? You cannot construct the class of all sets within ZFC. I mean, maybe you don't want to trust AI on this one, but like, you've just constructed it. The formula true? What do you mean the formula true? What do you mean by the formula true? You just can't. You can't construct the class of all sets within ZFC. I mean, this is the whole point of the axiom schema of comprehension. right? You want to avoid Russell's paradox. You don't want to be able to, I mean, okay, yes, that's a set of all sets, but again, the proper class, you're going outside the universe, right? It's like, here's an example. Think about ZFC without the axiom of infinity, right? Without the axiom of infinity, you cannot construct a set that has all of the natural numbers, right? You need the axiom of infinity to construct this collection. Even if you call it a class, even if you go and call it the class of all 0, 0, 1, 2, 3, this cannot be constructed in ZF minus the axiom of infinity. That's the whole reason why we have the axiom of infinity. Right, but this is what I'm saying. It's the meta theory that ZFC lives in, but you're going beyond ZFC if you want to work with that collection. If I want to take the category of vector spaces and perform manipulations between it, and I want to form the actual category, like what is the data of a category? It's a class. Well, a class is not within ZFC. You can't construct it within ZFC. Like, this is part of the meta theory. We talk about things while doing ZFC that are not in ZFC constantly. The formulas don't exist in ZFC. I'm not sure what you mean there. Well, anywho, let's move on. I mean, I'm gonna stick with AI on this one. You can't construct the class of all sets within ZFC. I mean, I don't know what else to say. If the formulas were encodable in ZFC. Okay, let's just move on. We've debated this point for a while. You were late today? Well, don't worry. There's like 6 hours left, a little over than 6 hours left in today's live stream. I'm team AI on this one. Yeah. I mean, I don't know. Do I go to Math Stack Exchange? Let's go to Math Stack Exchange. The discussion is not where interesting math lies. Well, depends. Set theorists might agree that there's set theorists might disagree. They would say this is where all the interesting math lies. Can you construct the class of all vector spaces, let's say all real vector spaces in ZFC? Would this be a good way to form the question? Unless you sleep for 6 hours. Have you considered construct the class of all sets in set theory ZFC plus AI? That could be the answer. Give an example of a thing you need GU for that you can't do with just ZFC axioms. Yeah. Not can you construct a class. How about the collection? What if I said the collection of all real vector spaces in ZFC? Joined by in ZFC, everything is a set. Yes, this is I agree. Yeah. So what about this? or how about this? Yeah, can we can you, how about this? Can you define the Hom functor from set to set in ZFC, right? Because this is my claim, because this is the data, right? Because this is the data. Oh, I thought I muted my group chat. Hang on one second. Yeah. You're happy with this way of the question? Hydrated. Categorically is hydrated and ready for math. Yeah, we're wrapping up the girls are fighting section pretty soon. Yeah. I mean, the contention is, let's say this is a contention. Can we define the Hom functor from set to set in ZFC? So let's put this in. So, to my understanding, everything in ZFC should be a set. Therefore, to even talk about the category set, one needs the category set in ZFC. One needs to describe it as a set. Actually, already here the so never mind the functor. We could actually change this to be, can you form the category set in ZFC? Can you define the category set in ZFC? Right? Can you define the category set in ZFC? To my understanding, everything in ZFC should be a set. Therefore, to even talk about set in ZFC, one needs to describe it as a set. In other words, the category, we might try to formulate the category as a triple, let's say ob, probably need to go into math mode here. So ob, and then a collection, math rm hom, math rm hom xy where this ranges over all pairs. Okay, what you call define is different from what we call define. Maybe this is the heart of the issue there. I cannot see how you would do this without some additional axiom of large cardinals. Exactly. So the resolution is that, well, using ZFC, we ask question and talk about things that aren't sets all the time. Yeah, what you were calling define wouldn't allow for defining truth. Okay. Just because one can write a formula that describes all sets, that doesn't mean ZFC proves there exists a set satisfying that formula. We're not saying there exists a set of all sets. You think the Hom functor is a good question? In practical terms, you can do stuff like algebraic geometry with just ZFC, is the practical question. So I think the answer is yes. I think the answer is yes, but not in the usual way that we define categories, right? So again, you can do linear algebra in ZFC. You can do linear algebra in ZFC. But if you want to manipulate the category of all vector spaces in the way that we usually define it, if you want to manipulate that as an object in the same way that if you can do all of Peano arithmetic without the axiom of infinity, but if you want to manipulate the collection of all natural numbers, then you need the axiom of infinity, right? Yeah, even Yoneda goes into size issues. You can work with category of sheaves just fine in ZFC. You can't do category of categories in ZFC. You can do category of vector spaces in ZFC. But how? But how? But you can't manipulate the category of vector spaces in ZFC. Right? You can't. How do you manipulate the category of all vector spaces in ZFC? Like in the same way, how do you manipulate the collection of all integers? How do you manipulate the collection of all integers if you don't have the axiom of infinity? But then how do you even say it exists? You can't say that something exists, right? Like, I can't say that the number two, I can't say it exists until I prove that it exists. And how do I prove that it exists? I mean, I define it as a set, right? So how could I possibly talk about the category of vector spaces if I don't prove that it exists? Right? You don't need to construct something within ZFC just to manipulate it. It's perfectly formal to prove the collection of sets is not a set. Maybe Arad's getting through to me with this comment. Hang on. Though the collection of sets is not constructible. Well, I disagree, Arad. I disagree. You can't prove that the collection of sets is not a set, because that doesn't make sense. Collection is not a formally, rigorously definable thing. You can prove that there is no set of all sets. You can prove the statement there is no set of all sets, because those are things you can actually talk about in ZFC. And for example, the axiom schema of comprehension allows you to show that you can't prove that. But the statement, the collection's not a vague word. So you can't form a collection and then prove it's not a set. What you can do is a proof by contradiction using the axiom schema of comprehension to argue that you cannot form a set of all sets. That is what you can do. You can prove that for all ordinals something holds. This I agree with. But the collection of ordinals is not a set. This I agree with. I completely agree with this. You can prove that something is true for all ordinals, but you can't. But the collection of all ordinals is not set. I perfectly agree with this. Yeah. So when you say G is a graph, you're literally working with a collection. What do you mean? A graph is a pair. A pair is a set. And what is a pair of? It's a set. It itself is a pair of sets where V is a set and E is a set. And in fact, E is a subset, is a specific power set of the subset of the power set of V. So a graph is a perfectly valid thing to construct in ZFC. So I don't know what you mean by like collection, right? It's a set. A graph is a set. It's a set. Subsets are a subset of collections. I mean, it's a set. It's a set. What is a collection? Like, what is a collection? This is a vague term. This is the whole reason why we have ZFC and axioms, right? The statement G is a graph, when you put it in first order logic, G is G such that phi graph G? Collection of graphs? No. We can define a graph. We can talk about graphs. We can prove something that is true of all graphs. We could write down a statement of the form, if G is a graph, ... and then we can go and prove things about it. That I agree with. What I don't agree with is that we can form the set of all graphs or the class of all graphs. I mean, what is a collection? This is even less defined. That doesn't make sense at all, right? Is it a set? Is it a class? How do you define logical connectives, within the axioms of ZFC? Yeah, I suppose that's something. I suppose that's something that comes from like the first order logic underneath it, right? Or that's part of the meta theory, I guess. Since you don't like the word collection. I don't like Leo collection or collection. None of these words make sense to me. Is the distinction between meta theory and theory actually well defined? That's a good question. Yeah, here's what I'm happy with. Sets. I'm happy with the word set. If you can construct a set, great. But collections, classes, ZFC, like even in first order logic does not talk about collections or classes, right? Like, yeah, yes, actually, so I agree. You could prove those things are naturally isomorphic. You can prove those things are naturally isomorphic. I agree with that. But to define a natural transformation, then you can't define it, because a natural transformation is what? It's a class, but I'd prefer to call it a set, indexed over all objects, right? And now this thing here as an object unto itself is beyond ZFC. We've gone beyond ZFC here. Can I show how to drive the character table from the algebra of a group's conjugacy classes? In a couple weeks. So yesterday, my first representation theory video came out. In a couple weeks, I will return to that. Yeah, I agree that you can give the transformation formula, but like to talk about I believe that you could do it. You can prove a statement like saying for all vector spaces, blah blah blah, that you can write down a map you know, for all triples of vector spaces UVW, you know, you can write down a map here that is, you know, a natural a map that's an isomorphism, like the associator for tensor products and whatever. Like this, I agree with, but I don't agree with the statement that you can construct the a functor as an object in ZFC. Yeah, if it's indexed over a class, it can't be a set. So, yeah. So. Right. I'm now starting to understand. So I agree that we can define a natural transformation in the sense that we can write down the rule that a natural transformation satisfies. I agree with you. I agree with you there. I agree with you there. But we cannot construct a natural transformation as an object within ZFC to be manipulated. So, yeah. That's what I would say. And this is the whole point of growth in deep universes, because we want to take things like functors and treat functors as objects and work with these objects and manipulate them. Like other and if that's not the case, then what is your interpretation of the very first axiom in this book saying that that we want the growth in deep universe? Like, why would we use that in your terms if that wasn't the case? Can we end friendship with set theory and go to type theory instead? Maybe that's the better thing to do. But I mean, if you want, but I think we do no, because to create the category of functors, to create like this, like if you want to form this category, right? If you want to form the functor category from set to set, you can't, not within ZFC, right? Is to treat functors as sets. Yes, I mean, I agree with that, because there are a lot of things we can do with sets that we can't do with general collections. With growth in deep universes, you cannot quantify overall functors, but you can still work with specific functors. I guess depends what work with here. In NCAT Lab, it says that ZFC is a first-order language. Yeah. Depends what work with specific functors means. Like, okay. Okay, we're over what you wrote down as a definition of natural transformation is second order. Yeah. You can define what functors are between sets, and you can define what natural transformations without needing GU. Okay. Well, I'm ending now, but I mean, do go get some food. Do go get some food, Arad. I'll end it now then. I'll end it now anyways. But yeah, go take a break. Go shower up. Go get some food. Maybe I'll have learned something about actual categories when I get back. Yeah. Well, I guess we'd agree to disagree for now, I suppose. I guess it comes down to, what it means to define and construct. Links do not work in chat. No, links do not work in chat. But if you want to tell us the title of the paper you're trying to link or something. Yeah. Okay, maybe should I go back and ask everything in ZFC should be a set. Therefore, the functor, therefore, given a set X, the functor math rm hom X dash from math rm set to math rm set should be formalized as a set. Clearly, this is not possible to do as, yeah. Where's Norman Wildberger when you need him? Yeah. Axiomatic set theory by Leinster. Maybe I should. Doesn't Leinster have some extremely weird views, some like extremely anti-set theory views or something that he's very aggressive about? Thank you, Anonymous. Thank you, Anonymous, for donating $5 to Children's Hospital and Research Center. Ultimately, that's what today is all about. It's about beefing about set theory and donating money to the kids. To my understanding, everything in ZFC should be a set. Therefore, given a set, the functor should be formalized as a set. Clearly, this is not possible to formalize as a ZFC set due to size issues. However, it seems that we can still talk about a formula which assigns to every set y and morphism f y to z a set math rm x to y and a function math rm hom x f from math rm hom x y to math rm hom x z. Let's see. Therefore, given a set here, the functor should be formalized as a set. Clearly, this is not possible to formalize in ZFC due to size issues. However, it seems we can still talk about a formula, which is assign. So while we can so it seems that we can still describe the data that defines a functor within ZFC, but is it the case that to treat f as an object unto So it seems that we can still describe the data that defines a functor within ZFC, but is it the case that in order to discuss math rm hom x as an object unto itself, that we need to go beyond ZFC with classes or large cardinals. This is a neutral question. Can you recommend the following? Ask the question, what amount of category theory can we rigorously do, only assuming ZFC axioms? Yeah, perhaps that's a good thing. Let me add that in here. Or are you saying I should make that as the title? Maybe I'll make that the title. The word object is a bit of a problem here. Well, why? Why? Let me say. So it seems we can still describe this as a functor, but is it the case that in order to treat a functor as a functor such as an, I don't know, entity, that we need to go beyond this? If we include the title question, yeah. What amount of category theory can we rigorously do, only assuming ZFC axioms? To my understanding, everything ZFC should be a set. Therefore, given a set, the functor likewise, if we wanted to form the functor category math rm set, math rm set, are we technically going beyond ZFC, as this itself should be a set if it's within ZFC? They get downvoted to oblivion. I mean, this might get downvoted to oblivion. Yeah. Yeah. Okay, what do I take this as? Set theory. Set. Wait. Set dash theory. Why is nothing coming up? Oh, there we go. Category theory. We need one more tag, right? So you would say that we need more than ZFC for the functor category, because you can't give a formula for formulas. So, okay, what if I change this to... So, again, I agree that we can define the notion of a natural transformation, but I don't think we can construct a natural transformation as an entity unless we go beyond ZFC. Likewise, it seems that we can describe the formula defining a natural transformation in ZFC. However, to talk about a natural transformation as an entity, it seems that we have to quantify over entity. We have to go beyond ZFC. Yeah, let's see what happens. Set theory, category theory, and what's the last tag I should put? Axioms or size issues. Size, universe, growth and deque universe. Universes, maybe. Maybe classes. Why are there no tags here? Proper class, maybe? Proper class? Proper class? How do we define, what else do we define here? I think you need 3 tags. Oh, it says add up to 5 tags. Maybe 2 tags is fine then. 2 tags is fine, yeah. You thought defining hierarchy of universes takes care of this? Well, that's kind of what led to the whole debate. Okay, reviewer question. Yeah. Post your question. Let's go. Boom. Okay. Now we wait. Because logic courses have to take, learn about size issues of category theory today. That's true. I could very well be wrong by simple fact of I haven't had a proper logic course on formulas. But again, I agree. I agree. We can write down formulas that define natural transformations, but we can't manipulate a natural transformation as an object without going beyond with size issues. Okay. Which infinity category theory textbook is this? Marcus Land. Well, I know that schema is technically infinitely many formulas. If we let top be the category whose objects are topological spaces and whose morphisms are continuous maps, the following are important objects. Topological n simplex. The topological n simplex forms a co-simplicial space, which sends n to that, where the induced maps are unique affine linear maps. Do what they should. Do what they should on vertices. You'll now shower and be back later. Okay. Well, see you soon. Get clean. More precisely, given a map here, we have an induced map on here. Okay. Yeah, geometric realization time. Geometric. How many people did we lose with this long debate where, maybe I'm wrong? Oh, we still, wait, let's see. I got to refresh to see how many people are watching. 36. Wow, we actually gained 3 people. Currently trying to understand Mandelbrot cascades. I've never even heard of those, TBH. But I'm glad you're liking the abstract nonsense. Okay, the singular simplicial set of a topological space is this simplicial set. It is the functor. It is the functor that sends... right. So the simplicial... Almost lost you. Sorry about that, Fimnal. Yeah. Sorry about that. It's the simplicial set of a topological space sends n two top homs from n top into X. Right. Makes sense. Geometric realization. Yeah, here's what I was talking about before. So I'm still confused about this notation. Speaking of, I'm reading Marcus Line. Maybe I should put this name of the book in the description. I don't know. Marcus Line's book on infinity categories. By the way, there's a nice general construction C to simplicial set given a co-simplicial object. Didn't we define co-simplicial object even? Or did I probably skipped that in the prerequisites. So geometric realization is the unique colimit preserving functor. Okay. So I guess if we go from simplicial sets from top and we say that this goes to here, I mean, is this enough to define a functor? Can we just define this and say, I demand that this preserves colimits? And then is that enough data to define the functor? I guess it gives it to us concretely. Concretely, the geometric realization of a simplicial set is the topological space. But why does this colimit always exist? Why does this colimit always exist? I guess you can just do it topologically, right? You could just take a union quotient out by relations, right? Yeah, okay, they give an even more concrete formula here, right? And this is something we struggled through, and I, spent like 3 days computing the topology of a genus 3 surface. Yeah. Cascades are a kind of generalization of fractal percolation to measures. The colimit definition of geometric realization is impenetrable. Yeah, I found it kind of confusing before as well. Because simplicial set is the presheaf category because all other presheaves are canonically a colimit. The representable ones, yeah. Hello, Woodrow John. Hello, Woodrow John. RP infinity? What's about RP infinity? I mean, that's a RP infinity's limit. Yeah. Because top is co-complete. Yeah. Well, but you still, I guess that's got to be proven at some point. But someone proved it, so it's proven. A proof is a proof. Did you know that, actually, so we've had all this debate about logic, and I don't know if you know this, but the smartest, the most correct logician in the world was actually a Canadian prime minister. I don't know if you guys know this, but I don't know if you guys know this, but
I don't know. A proof is a proof. What kind of a proof? It's a proof. A proof is a proof, and when you have a good proof, it's because it's proof.
Yeah, so that's the smartest logician that's ever existed, by the way. Canadian Prime Minister. Not the current one. Yeah. Hello, Seb. Yes, it's Marcus Line's book. Can we do an example of geometric realization with Z2 in RP infinity? What do you mean by that? What is Z2? The integers. Yeah, what do you mean by that? I think they're talking about. You're talking about like B, like forming like the classifying space of Z2, right? Forming the classifying space of Z2. Like somehow, yeah. Like somehow you take z mod 2 and you realize it as a simplicial set, and then when you take its geometric realization, you should get RP infinity, right? Yeah. I don't know how to do that, to be honest. Right, one object category. Well, how do we turn this? How do we turn this into a simplicial set? Actually, Rod, you might be able to help with this question. We want to turn z mod 2 into a simplicial set. So we want to go from delta op to set, and then right, we have to take the nerve. So maybe we should hold off on that until we go through the nerve construction. Singular set gives simplicial set. Yeah, maybe let's wait until we talk about nerves. Just because for myself, I want to review the definition of a nerve. Any set is a discrete simplicial set. Top of the morning to you, test demiazic. But sing is adjoint to geometric realization. Also, Rod, how do we form? What does it mean to be a discrete simplicial set? How do I turn this into? How do I turn? Let's say I have a set X, and now I want to define X bar, the simplicial set. So it should be a functor. It should be a functor. And where do I define on objects? Constant functor? Oh, yeah, maybe I just send it to X. I see. Right. But then somehow we want to remember the fact that Z2 is a group. Well, okay, again, maybe we should wait until I remind myself what a nerve is. What a nerve is. So, right, we do have some concrete realization of it here. Each element contributes 1 0 cell, 1 degenerate 1 cell, 1 degenerate 2 cell. I see. Each element of X. Right. The construction due to Milner. Here's how it goes from the colimit construction. Okay, I'll have to wait for the rest of the messages. Yeah, I think it shouldn't be that hard to write down, Ken. But I think I want to do a little more reading here. The singular complex. Wait. Right, the singular complex. Right, we defined up here. It's this functor. Is adjoint to geometric realization. Right. Yeah. The bar construction can give a simplicial set or a topological space or an infinity groupoid. I see. Okay, probably here's some definitions I'll want to write down. The claim is that the simplicial set given by the bar construction on Z mod 2 actually acting trivially on a point is cofinal among diagrams. Okay. Yeah, I don't know. I think I'm gonna have to read more before I get that. I forget the bar construction. TBH. Yeah, I mean in infinity groupoid. I mean, one of the ways to formalize it is as a simplicial set here, right? So the boundary is the sub-simplicial complex, which consists of non-surjective maps, whose k-simplices, right? So the boundary k-simplices is non-surjective maps. From k to n. I looked it up and instantly regretted it. Fair. And now the horn for any subset, the horn, the n horn, consists of those f from k to n, where there exists an I outside of S, which is not in the image of F. And then we've got inner horns and outer horns. Yeah. And then the spine are k-simplices, whose image is either of the form J or J plus 1. J and J plus 1. You needed this textbook earlier. You had to realize this characterizations of horns the hard way. Bro will internalize bar constructions before he does a single rep in the gym. Hey, I go to the gym all the time. Maybe I don't look like it at the moment. I haven't been going as much lately, but I go to the gym all the time. I drink my protein shakes. I go for my jogs. Although maybe not today. I'm going to be dead after 8 uninterrupted hours of streaming. Okay, let's look at some examples here. Let's look at delta 3, or what am I saying here? Right, delta, he claimed 4 times in a row. A web tool that lets one write in tech and live translate it to render tech would help this. Would help let my terrible writing. And not sparing space, yeah. Good joke, they sent. Good joke. Right, so delta... Right, but this is really a functor. Delta n. I mean, delta 2 is what? This is the functor. This is the functor into here, right? Delta 2 is a functor. No, maybe we should look at delta 3. It's a little more interesting. So somehow we should view this as right. And so if we look at the horn, so let's look at the let's look at 0, 3, and let's look at the, I don't know, 2 simplices here. So this is what? This is going to be maps from 2 into 3, such that there exists an I in 3 minus 0, where I is not in the image of F, right? Am I learning infinity categories? I'm trying. spinal catastrophism. Like I made a video on YouTube about it. What is spinal catastrophism? Should I look it up? I'll be honest. I'm probably not gonna watch it. I've already got too many things to watch. By the way, if you really want to use iCats in your work, you should probably ignore the simplicial set nonsense. You're probably right. But here we are. I mean, later in stream, I might switch over to like DG categories, and I might switch over to or trying to just learn about QCO on stacks or something. Yeah. So right. Wait, 3 has wait 0. Wait, doesn't this start at 1? Oh lord. Our ordered sets go from do we start at 0? Yes. Yeah, it's 0 to n, right? It's 0 to n. Yeah. You put infinity. Oh, you can put infinity stream in the name. I don't have to be cheap. Well, too late. So there has to be an I in 1, 2, or 3 that gets missed. So, right. Somehow I wanna view this in terms of like pictures. I want to be able to view this in terms of pictures like this, right? You only wrote lambda 20 in your notes. Yeah. Well, I guess I need a 0 here as well. Yeah, maybe I should have done lambda 20. That's easier to picture. So lambda 202. Let's make life easier on myself here. I'm gonna be cheap. Infinity over 1 reps performed this year by mathematician YouTubers. Hey man, I've got a whole maybe we'll need to switch over to Keratin as well. I've got Excel spreadsheets. I track all my reps, every set, track it all. If I know basic drive categories, then I can switch to infinity categories via stable infinity categories. Yeah, maybe that's what I should do. But here we are. Nonetheless. Okay, so what sort of maps do I have here? Well, what could I do? There has to be either 1 or 2 has to get missed in this, right? Either 1 or 2 has to get missed. So fake alibi stacks up more and more. Oh, maybe next time, I'll go live stream from the gym. How about that? So we could send 0 to 0. We can't do this because then something wouldn't be missed. But I think we could do this. I think we could do this. I think we could do this goes to 1. And then the rest would have to go to 1 because they have to be bigger and we can't miss anything. And then this could go to 2 and then this could go to 2, right? Am I correct in thinking that these define all the... is this right? I'm taking bathroom break number 1 of the day. So you guys gotta... now that you've criticized my decisions, what am I trying to show? I'm trying to just describe this horn, this outer horn, in one particular example. But I'll be right back. Entertain yourselves. Oh, it might also be time for some food soon. I don't know. Getting hungry. Have some food, and then maybe maybe people have yelled at me on Stack Exchange, so we can just spend some time reading what people have said while I eat. Yeah. Yeah, I don't know. Okay, should I go over to Carradine now? I mean, we've spent a lot of time looking at these prerequisites and with being confused. Well, let's go through some of this. Actually, I do want to review. Okay, the nerve of a category. Let's review some things here. So the nerve of a category. What do we got? The nerve of a category is the simplicial set given by sending n to the functors to the set of functors from n to c. It's given by taking functors out of the previous co-simplicial category to the given category. Wait, and I'm treating n here as a category, which is true, I guess. It's a category with n+1 objects and a unique arrow from I to j if I is less than or equal to j. This is making you nervous? Why? Because I might start complaining about sets again, set theoretic issues again. The nerve of a category is a simplicial set given by this. Right. And this is isomorphic to no, because in there. Oh, I see. Oh my god, I can't believe I missed that very obvious pun. But I'm a little confused because here the HOM is taking place in the category. Right? Are we really treating n as a category? And we're looking at fun as in functions? Wait. No, that doesn't make sense because he's a category. It must be functors, right? Right. So treating both of these as categories, I guess the functors between them are just HOMs in delta. Right. Fun as in functor, yeah. Because functors are fun. So, delta n, right, delta n is just the nerve. The nerve of some people is the nerve of this category. Therefore, aha, so here we go. The classifying space of a group is the geometric realization of the nerve of the group considered as a groupoid with one object. Right. Okay, great. So, right. So now maybe we can talk about this exercise. So we take the group. I'm going to write it as C sub 2 because I am. And now I'm going to write the underlying here. I'm sure someone's mad about this notation for some reason. Right, the poset category, yeah. So I'm going to write C2 underline. Now this is the one object groupoid. And now I take the nerve. Now I take the nerve of this. And the nerve of this is now a simplicial set. The nerve of this is now a simplicial set. It's now a simplicial set. Yeah. And I want to take the geometric realization of this nerve and see that it should be RP infinity, right? So the geometric realization of this is going to be what? So let's go back a little bit here. So, I mean, looking at this really concretely, to be honest, looking at the bar complex of any group explicitly, even Z2 gets unwieldy. Have I read any Carradine? Well, we might switch over to Carradine soon. I think I want to get to like the first definition of an infinity category is here, and then maybe we'll switch over to Carradine. Yeah, is this just gonna be too unwieldy? Yeah, maybe is this too unwieldy? Is there a nice way to see this? For all n in here, the nc2 at n cross delta n top modulo the relation. Right. And what is the nerve? Nerve of C2 at n is going to be, yeah, too unwieldy. Okay. Hom from here into what? Into C2 the groupoid. You recommend just draw the non-degenerate simplices? I'm not sure I even understand how to do that, to be honest. I'm not even sure I understand how to do that. I mean, in this case, it's a one-object groupoid, right? Oh, no. Woodrow John said no. Okay. So on objects, but I mean, am I wrong? Did I do something wrong here? I mean, this is how it's defined, right? Unless I'm incorrect about my definition. It is all composable elements of C2 of length n plus 1. It is all composable elements of C2. All composable elements of C2. I see. Technically, wouldn't any n simplex for n bigger than 1 be degenerate? Yeah, I mean, Hom, let's say, from 0 to C2. I mean, this just has the identity on it, right? So it just sends the identity to the identity. So that's uninteresting. If we look at Hom 1 of C2, then really I just need to think about this my arrow from 0 to 1. I mean, I also have my identity arrows. But then hello again, Connor Melly. Hello again. You're right, Leo, I am degenerate. But then I send this to some. Well, I have various choices, right? So now I could send this arrow either to the identity of C2. Could I send it also to the non-identity in C2? Oh, that was a response into something else. Yeah, sorry, there is a lot of a lag going on. What are we doing now? I mean, we've come to the definition of a nerve, and I'm trying to understand why the geometric realization of the nerve of the groupoid determined by C2 is RP infinity. Thank you, Frenzy. Thank you, Frenzy, for your donation. So, yeah, thank you very much. Good time to remind everyone this is a charity fundraiser for Children's Hospital and Research Center. So, yeah, it's please donate. Please donate to help the kids. HOM1 C2 is in bijection with C2. Right. Makes sense. Yeah. Okay, but now how could I possibly begin to see the structure of RP infinity here? I mean, for each n, should I not be seeing like an RPN or something? And only half goes to Leo lectures. Which is a joke. Just to be perfectly clear. 100% of the donations are going to the kids. Yeah. So I don't know, but people are telling me this is hopeless to try and realize this now. So I don't know. Geometric realization of a horn is a horn. A spine is a spine. Oh, I think we looked at that already. Okay, so a Kahn complex. Very important definition for us. These don't look like Dahas. This is accurate. They do not look like Dahas. I agree. Yeah, who does look like a Daha? Thank the Lord. Yeah. The Kahn complex is a simplicial set which has the extension property for horn inclusions. Right. A Kahn complex has the extension property for horn inclusions. The singular complex of a topological space is a Kahn complex. Proof, we do an adjunction. We suppose I see. The two lifting equivalents of two lifting problems. Now recall that a topological horn inclusion has a retract so that the right lifting problem can be solved. What does that mean topologically? Hey girl, you spine hella fine. Can I make it mine? We need to hear the full song. Drop on your channel. You think the nerve of the category B of Z mod 2 is the diagram? I don't understand that. Yeah, what does this mean in geometric terms? Like if I have a filled in triangle and I have a horn is something like this, right? A horn would literally be something like this. And I have a map into my topological space. And Woodrow John, the nerve of that category is the diagram. You have to remember I'm very slow. Ooh, $14. $14. Thank you to Anonymous for your donation. Thank you very much to Anonymous for your donation. I think that puts you. We've got a lot of people tied for first place donations. I think this puts you squarely in second place. If drawn correctly, the first step 0, 1, 2 should get you the drawing of RP infinity as a triangle with edges identified. Then hand wave the rest of the cells, destroy the higher holes. I believe you. I just don't completely get it. Yeah, Nikolai, we need the full rap. Maybe we can have a collab. We can write the rap together. I'll write a little piano thing so someone can make the beats. Yeah, I think are we over $100 now? I've already lost track. I think we're over $100 now. Yeah. You should stream from hospital and teach children infinity categories. We're trying to get them to get better, not make them worse. Not make them worse. Okay. Right. So what does this say? This says that we can fill in this map. It says that if I have this map, I can fill it in somehow. Can we always solve this lifting problem? I guess. I don't know. Yeah. Is my picture right? Can we solve it? We're at the filling portion of the show. Yes, exactly, Leo. Absolute value. That's the geometric realization. Although lambda into delta looks nice. Yeah, it's just inclusion, right? I think this is the exercise I was thinking of. This is a good one to do. This is a good one to do, right? If the nerve of a category is a concomplex, then the category is a groupoid. So, right, we need to take... So I have some category, C. I have a map from X to Y. And I want to show that this is an isomorphism. And I'm going to suppose that the nerve of this category is a groupoid. And this says it comes from lifting of outer two horns. So I should be looking at outer two horns. And it should say for every map here, and here's my inclusion into delta 2, I should be able to complete this. Yes. And I've done this exercise once before, so this is kind of cheating. Did I see the quanta? But remember, there was an exercise that I said I did once before, and I also spent like 30 minutes and gave up. So, did I see the quantum magazine thing that string theory solved an algebraic geometry problem? Isn't string theory always solving algebraic geometry problems? Maybe they did a big one. Can't find the archive paper from the announcement. Maybe it's just been announced and the preprint hasn't dropped yet. Okay, so let's see. I somehow... Right, so I have X and Y here. And so what do I need to do? I need to define... I need to set up the morphism here that's going to fill it in. And I know that what I need to do is I need to think about like some... I know I need to think about like some triangle. No, that's the map I want to get out. I know that the picture I want to make is something like this, right? I want to think about this as like being my two horn somehow, where this is the identity on Y and this is F. And then, oh wait, but maybe this is the wrong way. Maybe this is the wrong way. Because I want the map to go from Y to X, right? So, darn it, which way does it go? So maybe Y goes here X goes here, X goes here. It's something like this, right? And now somehow, right, the inner horn filling should give me my map here. Yeah. Draw the triangle with F on the top left, right, and identity on the bottom. Right. This is, yeah, because this is 0, 1, 2, and then it's the 0 horn because we're missing this thing. Right. Right. And so, but just to be a little more precise, how do I define it from the horn? Well, I guess I've defined it, right? So eta should be the natural transformation that sends 1 to y, 0 to x, and 2 to x. And then it sends the morphism from 0 to 1 to f and the morphism from 0 to 2 to 1. Yes, this is an outer horn, exactly. Is that not just a retraction? Maybe? I don't know. Supposedly your Skeen stuff is closely related to string theory. Yeah. Raymond's gonna solve string theory with Dahas. Right. And so the horn, right, and exactly. So the horn filling basically says that now we get this map everywhere here. So it says in particular we should get a map that makes this diagram commute. Yeah. Yes, and then yeah, you're right. We would use we did the 0 horn, and then we need to do the outer 2 horn. Absolutely not. Yeah. Okay. Yeah. So I think we might go over to Keratin right away. I wanted to revisit that exercise. Though this is a crazy statement to me. If n is bigger than 4, and for any category, you can solve the lifting problem uniquely. You will be leaving. Well, thanks for stopping by. And I'm glad that you appreciate the channel. That is fine. Hey, so if it's not available in your region, just a reminder, then I would just ask anyone who wants to donate, but it's not available in your region, just donate, whatever you were going to donate to like your local children's hospital or some similar kind of charity that you care about. Just using it as an excuse to send off a donation. Doing homework, you got lost. What's inner and outer again? This has nothing to do with measure theory. Different use of inner and outer. Yeah. Actually, I'll be honest with you, the skeletons and co-skeletons scare me. I don't understand this stuff at all. Yeah. The nerve of a category is a complex if and only if C is a groupoid. Yeah. Okay. Infinity categories. So I think what I'm going to do, I'm starting to get hungry. So I think I'm going to go heat up some food, and then maybe we'll see what hits I've got on Stack Exchange. So let me go heat up some food. Okay, I got some food heating up. What's a sign of weakness? Landsbook. You wish you could keep up with the stream, but it seems like stuff in category theory and context is a prerequisite. Well, maybe some of this stuff will seep into your brain anyways. Yeah. Okay, composer is an important tool, I guess, but where's our definition here? Let's just look at our definition. Confused by everything. This is actually probably something I should really sit down and understand, is this statement here, actually. Because this has to do with the homotopy equivalence relations and stuff. A simplicial set, right? A simplicial set is called an infinity category. A simplicial set is called an affinity category if it has the extension property for all inner horn inclusions. So simp is infinite if inner horn filling. Right. A functor between two infinity categories is just a map of simplicial sets, which is to say it's a full subcategory of simplicial sets. Okay. Let me go. My food's still heating up. 1 second. Okay, do we go over to keratin? Do we go over to keratin now? Maybe. Keratin. Examples of infinity categories. Differential graded categories. I definitely want to go over those. But this is a good place to go, right? Examples of infinity categories. Why don't we take a look at this? Chapter 1, we introduce infinity category, simplicial set, which satisfies the weak con condition. The theory of infinity categories can be understood as a synthesis of classical category theory and algebraic geometry. Topology. So, every ordinary category can be regarded as an infinity category by identifying C with the simplicial set of its nerve. Right. And I guess we proved a theorem that the nerve of any category, right? Didn't we just look at that theorem? The nerve of any category. We just had a theorem about the nerve. Wait a second. The nerve is a con complex if and only if it's a groupoid. But I guess we have a theorem about the inner horn property, right? Maybe we didn't get that theorem down here yet. Yeah, I guess, and we want to look. H is the homotopy category, right? Kind of want to look at that as well. I mean, I guess it's in keratin. Let's just go to keratin. Wasn't it just 1.1.50? Was it? Wait. 1.1.50. Oh. 1.1.50 is the that's the definition of the homotopy relation. Right. We say that. Okay. Oh, you meant for the definition. Right. Yeah. I still find this a little confusing, but let me go get my food and then let's go look at stack constraints to see how wrong I am. Got to get a bunch of hot sauce going. Yeah. Okay. Well, Professor John Smith, it's not actually a matter of being clever. It's not a function of being clever. It's just a function of the background you have. Well, maybe it is partly a function of being clever, but you're probably clever enough. You just, how do I cook so quickly? Because I cooked the food yesterday and I'm just heating it up today. Maybe I should move the mic further away so you don't hear all the mouth sounds of me eating. You might anyways. Let's see, how wrong am I? Oh, I got a lot of 19 points. Oh, no responses yet. Wow. Cooking it yesterday seems clever. Yeah. Did I cook enough food to get me through all the stream, though? Well, next time I get hungry after this, I'll probably make a protein smoothie or something. That won't take very long either. Yeah, no answers yet. Okay, but no downvotes. Yeah, so that's fine, I guess. Yeah. Okay, every con complex is an infinity category. In particular, a simplicial set of any topological space is an infinity category. Right. Infinity category can be regarded something that encodes information not just about objects and morphisms, but also about homotopies between them. Definition 1.4. Okay, maybe we should go there. When C is the nerve of an ordinary category, the notion of homotopy is trivial. I see. On the other hand, if it's a con complex, then every morphism is invertible up to homotopy. Our goal in this chapter is to supply a larger class of examples of infinity categories, which are more representative of the subject as a whole. Okay, maybe we should go over to this definition first. Oh, right. Okay. So C and D are infinity categories. A homotopy from F to G is a 2 simplex of C There's a 2 simplex of C, which has, maybe I want to draw a picture here. So which has 0 to 2, 0 to 2 equal to the identity on D. I'm already confused. This is going to be something like for each small object in D, this will be like the identity here, right? And then the arrow 1 to 2 will be G. Wait, no, now I am confused. We're almost halfway through. This isn't as bad as I thought. I thought this whole thing would just be pure torture the whole time. Probably I shouldn't have spent so much time arguing about set theory, because we should really be further along by now, but oh well. Yes, exactly. Morphisms between morphisms. Well, the diagram's depicted for us here. I see. It's a 2 simplex of C. Wait. Okay, great. Yes. Okay, sorry. I'm back on board. This makes sense. I was thrown off by misreading the cal C. Does that mean I'm going to do another 8 hours afterwards? Certainly not. Let C be an infinity category, and let this be a pair of morphisms. Okay. Makes sense. Yeah. Checking in on things here. Okay. There are always more hospitals to stream for. That is true. We'll see how successful this stream pans out. Yeah. Can I raise more than minimum wage would have raised for these for this charity? Because otherwise, if I can't, well, actually, no. I think we've already raised more than that. What's minimum wage these days? Canadian minimum wage in Calgary. Probably more money than I make annually. Minimum wage in Calgary. Okay, 15 an hour. So, yeah, I guess we've pretty much we've probably raised a minimum wage amount of money already. So actually, it's worth it. I don't know. Being a professional math streamer seems like it would be a perfectly fine life. I wouldn't be upset about that. Federal minimum wage $7. Yeah, but $7 American is $4,000 Canadian, right? It's about $4,000 Canadian. Yeah. Okay. So you guys are still poor compared to us. D02 is the map. Like we have like I guess if we're in delta 2, right, we have gosh, what's the right way to say this? I mean 4,000 Canadian rubles, yeah. Like D02 is this map. It's this map, right? It's this map. Because this is like the poset. Well, I mean, this thing should be this is the functor into 2, where 2 is the poset category with objects 0, 1, and 2. and this goes from 0 to 2. Except I guess actually when we write 0, 0, 2, I guess we're thinking about like we're creating an object, like we're thinking about like applying this functor at an object. Why is bro still on Simplicial set? Because I'm not that quick. I'm not that quick. Okay, we're going to get on to a larger class of examples now, which are more representative of the subject as a whole. Okay, I'm probably going to read quietly for a bit while I eat. Yeah, it's the image of that morphism in the two complex. Yeah. Enriched category. Let A be a monoidal category, vector spaces. Then an A enriched category is a mathematical structure. That's an object of A. We have a composition law. Blah blah blah. 3 examples of this paradigm. Let A be the category of simplicial sets. So what's the monoidal structure here on simplicial sets? Like I have 2 functors, x and y, into set, and I guess what x tensor y is just the Cartesian product. I just go y in and x in. Like on objects, I guess. Yeah, the 2 is the dimension of the domain. The 0 tells you the face opposite to the vertex. Wait, what would smash product mean here? Day convolution? I don't know that either. Wait, what's a simplicial category? Oh, sorry. A category enriched in simplicial sets is a simplicial category. Right. And to each simplicial category, we associate the homotopy coherent nerve. Moreover, we show that if each of the simplicial sets is a Kahn complex, then the homotopy coherent nerve is an infinity category. Okay, but that definition's coming up. Oh, here's one I like. Here's one I want to understand. The category of chain complexes of abelian groups equipped with tensor product. Okay, categories enriched in that are differential graded categories. So we associate each differential graded category, a DG nerve, and we show that that's always a category. Back to size issues, a category of small categories equipped with the monoidal structure. You formally back up Raymond. In this case, we refer to an abelian. Or sorry, what am I talking about? Oh, I'm tired. Almost halfway through. A special case of a more general notion of a two category. Right. Sorry, what are we looking at again? The category of all small categories. Monoidal structure given by Cartesian product. Right. As a strict two category. We'll associate to each two category the Duskin nerve and show if this is a groupoid, this is an infinity category. Okay. I appreciate Leo as well. Coffee pour over ASMR. I finished my coffee a long time ago. Where's just the next page? Yeah, let's go to next. Get out of here, Acrobat. Becomes coffee and jumping jack stream if the streamer gets tired enough. Well, I'm not. It's too late in the day already to have coffee. I want to sleep tonight, but jumping jacks maybe. But I just ate. I'm probably gonna go grab a banana and a protein shake in a minute as well, because I don't know if that was enough. But yeah. Something funny you saw recently was that a two category is just a monoidoid. Yeah, I saw something modulo some oidoids. I saw something like that too recently. Monoidal monoidoid. Oidoid. I'm one of those responsible caffeine consumers. Yeah. Definitely didn't always used to be, but I've gotten frail in my old age and delicate. So if I have too much coffee, I don't sleep well, and then I get cranky. Every complex. Actually, I want to go back to what is the definition of infinity groupoid in land? Oh, maybe if I spelled groupoid correctly. All right, how's he define a groupoid? Oh, infinity groupoid though, actually. Okay. Let's go until we find infinity group. An infinity category is called an infinity groupoid if every morphism is an equivalence. And what does it mean to be an equivalence? It's an equivalence if the image in the homotopy category is an isomorphism. Okay, so we need to understand the homotopy category. Sorry, I'm back to land. But I do want to look this up for a second. Your academic sister wrote a blog about monoidoids. A monad is a monoid over a category of endofunctors. Yes. A monad is a monoid in the category of endofunctors, I believe. Have you ever seen Doodle Bob? He's basically a category theorist by the oidoid standard. No. If you want a really funny Stag Exchange thread, look up Can't Argue with Success, looking for bad math that gets away with it. Okay. I'm worried that this will distract us too much from the main point of the stream, but this is actually pretty tempting. Okay, this is pretty tempting. Oh yeah, okay, I see. Yeah, I've seen these sorts of things before. There's some like fun ones. Yeah, there's some fun one with sine I remember seeing. Yeah. What's the how do we find the page? How do we find the write-up? What am I looking for again? I'm looking for the definition of equivalence. No, I'm looking for, yeah, to the homotopy category. Which was like somewhere up here, I guess, right? Right. We form the category HX by means of generators and relations. The objects are given by the 0 cells. The morphisms are generated by X1. For every one simplex, there is a morphism. For every one simplex, there's a morphism between those two objects, D1 to D0. Wait, from D1 to Z0? Shouldn't it go the other way? Free composites will be denoted by that. Wait a second. Morphism from DF1 to DF0? Shouldn't it be the other way around? Or do I have the degeneracy maps incorrect? Because, I mean, this is what? This is really just like, this is like a pair. This is like, what? F at 0. Morphisms are generated by X1. I mean, should this be F0 to F1? Shouldn't it be F0 to F1? Am I crazy? Yeah, I'm talking to you, Raymond, about the write-up. You said your academic sister had some write-up blog post about monoidoids. What's the name of the blog? There's a morphism. Yeah, why do I have this backwards? It's from D1 to D0 because D1 takes you the vertex opposite. Okay, great. Okay, I see. Right, so that checks out. Right, and then we make free composites, and then we say the one simplex. Right, S0 is the identity for every two simplex with boundary for every two simplex with boundary given by a triple. FGH. I'm a little confused by this. We impose the relation. I see. So we're just, I see. That's just saying that, relations are as they are in the category. But then also we say we impose these other relations. If F is homotopy equivalent to F, then we demand these are homotopy equivalent. Where homotopy equivalent means right, if there's a two simplex restricting to both of those. Chris Grossack? Is that the one Raymond was talking about? Okay. Right, so that's the homotopy category. Functorial. What are some things we should know about it? I guess we want an equivalence of infinity categories, right? Where was that? The homotopy category of the nerve is canonically isomorphic to the original category. And so we have the pair of functors. Nerve and homotopy are adjoint. Right, where the co-unit's given by that. And then a morphism in an infinity category is an equivalence if its image in the homotopy category is an isomorphism. Okay. Monoidal, monoidoidoids. Monoidal. Yeah, maybe if I just search that. Monoidal, monoidoidoids blog. Chris Grossack's blog. You're on NLab, 2 categories, just a monoidal, monoidoid. Scrubs of joy, and telling X is just a yeah. Monads are just monoids in the category of endofunctors. Yeah, classic. I think we should maybe I'm gonna keep this open, but maybe we should read it later. I kind of want to stick to the main thing. But why is a category just a monoidal monoidoid? Yeah, maybe we'll read this. I don't know, tomorrow or something. You're wondering how you oid something already oided. Yeah. Why not keep going? Why not keep going? Okay, so let's get back to Lurie here for a second, or Keratin, I should say. I mean, it's not purely Lurie, right? Although I guess a lot of this is him, but it's a group effort. Monoidal category suspension is a 2 category with 1 object. So if you have many objects, you have a general 2 category. Every Kohn complex is an infinity category. Wait, why are we here actually? I want to go back. I think we're on. Oh yeah, this is section 2 stuff. Oh, I guess we have to click through the other parts of section 2 on our own, or what's going on here? Yeah, where do we go? Where do we go from here? I guess differential graded categories is one I really... Well, homotopy coherent nerve. So we should go over to 2.4. 2.4. De-looping, not suspension. Leo distracts me a lot from being productive. Well, I don't mind it. I don't mind the distraction. Maybe you guys need to be working harder to distract me. Basil fried rice, nice. Apparently suspension operators on homologies are related to Daha. What area is this? Infinity categories. Category theory and homotopy theory, basically. Okay. The homotopy coherent nerve. Let C be a simplicial category. We write this to denote the simplicial set given by the construction. Well, I don't know. We need to read more things before this, I guess. Simplicial categories. Okay. Let top denote the category of topological spaces. By definition, a morphism in the category top is a continuous function. In homotopy theory, one is fundamentally concerned not only with continuous functions, but homotopies between them. So, whoa. For n greater than 0, we consider the set hom top be continuous functions from there. And then the sets can be assembled into simplicial sets. I mean, is that equivalent? Is that equivalent to continuous functions from x to y? This weekend, your thesis advisor just gave a course on infinity categories for undergraduates, and it didn't go as bad as one could possibly expect. That's pretty high praises, I suppose. Yeah. Topological simplex of dimension n. The sets can be assembled into a simplicial set. And the construction endows top with the structure of a simplicial category. Right. Much as the singular set can be regarded as combinatorial encoding of homotopy theory of an individual space, the simplicial enrichment of top can be regarded as a combinatorial encoding of homotopy theory of topological spaces. Okay. Our goal in this section is to provide an introduction to the theory of simplicial categories. We begin in 2.4.1, defining the notion of a simplicial category. Recall to say the nerve. Recall that to every category we associate the nerve. In 2.4.3, we describe a generalization of this construction, which associates to every simplicial category a simplicial set called the homotopy coherent nerve. This construction specializes to the ordinary nerve in the case where C is an ordinary category, and to the Duskin nerve when it's a strict 2 category. Okay. Okay. So, yeah, maybe we just go back to the homotopy coherent nerve now. Let top denote the category of topological spaces, and let the nerve of top denote its nerve. Then this is a simplicial set whose 2 simplices can be identified with diagrams of topological spaces. In the study of algebraic topology, we have weaker things. In this case, we say, yeah. So we will introduce an enlargement of the simplicial set whose 2 simplices IC are given I see are given by pairs sigma and H, where H is a witness to the homotopy commutativity of sigma. Sigma is one of these triangles. Okay. Right. And I guess that makes sense in, like, for infinity, or I guess simplicial categories more generally. I guess how do we formalize the H, though? I guess how do we formalize the H more generally? I guess that's what we're going to see. So, study of algebraic topology, one encounters diagrams which commute in the weaker sense. Yeah. Simplicial path categories. This is something we need. Okay, so say we have a poset, and path 2 of Q denotes the path 2 category. We didn't look at that. The path 2 category of a partially ordered set. We define a strict 2 category. So the objects are the elements of Q. The given two elements, denote the partially ordered set of all finite, linearly ordered subsets of Q that start at X and end at Y. Ordered by reverse inclusion. We regard the partially ordered set as a category having a unique morphism from S to T whenever T is contained in S. For every element, wait, why is this a two category? What's our two morphisms? Oh, we have a unique morphism from S to T whenever it's included in there. Okay. Okay. Then, oh wait, simplicial path categories. Right, we let path Q denote the simplicial category obtained from the strict 2 category by applying the construction of this example, which we also skipped, but he's going to lay it out for us. So the objects of this are elements of the poset. Okay, he's just re-outlining the construction. Now I'm a little lost. Objects obtained from the strict 2 category by applying this construction. If we have a strict 2 category, then we can associate a simplicial category, which the objects are the objects for every pair of morphisms. I see. Right. Okay. So the Hom set is itself a category, and so we can actually assign it the nerve of that category. Okay. Drawing down the examples for n equals 2 and 3, you should get a filled triangle. Maybe you're right. But okay, I think he's going to say writing down. Or drawing down, writing down. Yeah. I know what you meant. Yeah. But I guess this makes sense to me. If we have a strict 2 category, your Hom sets are categories, and then you take a new category where you take the nerves. Cat category sounds a lot cooler than 2 category. Yeah. Well, let's start using it. Okay, so this is a 2 category. We form the simplicial category, or the simplicial category out of it. Okay. Okay. Relationship with ordinary path categories. This is a post set, and we let this be the associated directed graph. Then the path category is the underlying category of the simplicial category. And otherwise, we can view it as a simplically enriched version of path graph. Okay. Oh, okay. Sorry, bumping the mic if wearing headphones. Hopefully I didn't screw up your ears. Let C be a simplicial category. We denote the homotopy coherent nerve. We let this denote the simplicial set. Okay. defined by the construction. We send n to, okay. We send n to the path, the associated path simplicial category. And then we look at the Hom set of Homs between simplicial categories of that and to C. Okay. I don't understand, but I do. I don't understand, but I do. So the homotopy coherent nerve, of C is the simplicial set sending n to Hom path n as a simplicial category to C, the simplicial category. Okay. Let's see. So the homotopy coherent nerve determines a functor from the category of simplicial categories to the category of simplicial sets. Sure. Yeah. Okay, where are we here? Let's go back to chapter 2. 2.4 is simplicial categories. Okay. I feel like I've understood half a thing now. Dold-Kahn correspondence. We want to get there. So let's look at differential graded categories. Okay. 12 o'clock. We are halfway through. Everybody. So now's maybe a good time to remind you that this is a charity fundraiser live stream for a children's hospital and research center. So if anyone can donate, it would be greatly appreciated. Let's raise as much money as we can. Let's maybe, I want to see how many people we got watching right now. Watching stream 24. We lost a few people. We lost a number of people. That's a long day. That's fair. Let's go see. Let's maybe pause for a moment and go see if anyone's explained to me if I'm wrong. We got 3 upvotes and we still have no answers. Okay. 3 upvotes and we still have no answers. Okay. Should I go refill on some food real quick? Quite possibly. Monoidoids. Okay. Differential graded categories. Let this be the category of chain complexes of abelian groups equipped with monoidal structure. A differential graded category is a category enriched over chain complexes. Okay, great. Great. That is fine. Differential graded algebras. A differential graded algebra is a not necessarily commutative graded ring equipped with a differential and a Leibniz rule. If C is a differential graded category containing an object X, then the composition law on C endows the chain complex of endomorphisms with the structure of a differential graded algebra. Well, what? Our multiplication is going to be like... our multiplication is going to be composition, right? But what's the addition? Oh, I guess because I guess we have addition because it's chain complex graded. And I guess right. Yeah, it's enriched in an abelian group, so that's where our addition comes from. Conversely, for every differential graded algebra, there's a unique differential graded category with a single object, X. So differential graded categories are differential graded algebroids. I'll take your word for it for now. In other words, the collection. Oh, maybe that makes. I mean, an algebroid is just like a groupoid, but now you've upgraded it to an algebra, right? In other words, a construction C to this induces a bijective correspondence from differential graded categories with a single object to differential graded algebras. Okay, nice. So B dot chain Z denote the classifying simplicial set. What? The classifying simplicial set of the monoidal category of chain complexes. Was that defined somewhere else? For each non-negative integer, we can use the analysis of this remark to identify n simplices of this with differential graded categories with n objects, and the Hom sets are this. Okay. Functor should, I guess respect grading or something and give us like maps of complexes. Okay. Oh, this is like the overview page for differential graded categories. Simplicial abelian group. Okay, let's read this. Oh, and the differential graded nerve. Okay. Heuristically, one can think of this data showing C with the structure of a higher categories whose n morphisms are given by elements. Here, we make this heuristic precise by constructing a simplicial set called the differential graded nerve of C, and proving that it is an infinity category. Then we show that the homotopy category of this can be obtained directly from C by identifying homotopic morphisms. In particular, the homotopy category can be identified with the actual homotopy category. Okay. Let's just have a little peek at this definition. So the differential graded nerve is the simplicial set whose values on an object is the set of construction here, whose value on a non-decreasing function is the function. Okay. For a differential graded category, the differential graded, the nth part of the nerve, the n simplices of the differential graded nerve, are ordered pairs from 0 to n with f, where each xi is an object of the differential graded category. Each xi is an object of the differential graded category. Right. And for every subset of n having at least two elements, f is an element of the abelian group. Okay, if it's k things, then it is the k minus 1 part of simplex of this thing satisfying this identity. Okay. Gang, I'm cooked. I'm a little cooked right now. I'm not going to lie. Okay. Okay. This post was made by Homotopy Gang. Yeah. The remainder of the section is devoted to studying the relationship between differential graded nerve of a homotopy and the homotopy coherent nerve. This will require a somewhat lengthy detour through the theory of simplicial abelian groups. In 2.5.5, we'll associate to each simplicial set its normalized chain complex, given in each degree by a free abelian group on the set of non-degenerate n simplices. This construction determines a functor from the category of simplicial sets to the category of chain complexes of abelian groups. We show that this functor has a right adjoint. Okay, the functor has a right adjoint from chain complexes to simplicial sets, which is the Eilenberg-MacLane functor. To each chain complex of abelian groups, this functor associates a simplicial abelian group, which we'll refer to as the generalized Eilenberg-MacLane space. And the Dold-Kahn says that this is an equivalence. Okay. Maybe this is a time to go over. I have a little PDF that's maybe more meant for babies like me on the Dold-Kahn correspondence. So why don't we read this random PDF for a little bit? Why don't we have a look at this random PDF for a little bit? And then maybe I don't know, maybe at some point we switch over to who was it? Someone said that it's better to just like look at infinity categories in action. And yeah. So maybe we should go and try and understand like the infinity category QCO. I think it was Woodrow John who was saying this. So maybe we should just go like stare blurrily at QCO. Simplicial sets are equivalent to chain complexes of abelian groups. Oh, I don't think that is the case. I think simplicial abelian groups. I think it's something like simplicial abelian groups. Yeah. Simplicial abelian groups or something. Yeah. Okay. Where am I here? Simplicial abelian groups are equivalent to non-negatively graded chain complexes, right? Okay, let's see what this random PDF has to say. Right, simplicial set, topological space, classic stuff, which we've been over. Generalities on presheaves. Oh, maybe this would make me understand that thing I wasn't understanding before. Right. Let F be presheaf for each object. Let this be representable presheaf, defined by this. Now form the category D, whose objects are morphisms of presheaves and whose morphisms are this. Note that these commutative diagrams depend on nothing fancy. A morphism here is just a map from X to Y in view of Yoneda's lemma. There is a functor from hang on a second. What's this other category D here? F is a presheaf. Right, D is this category. Now there's a functor from this category to presheaves that sends an arrow hxf to hx. The image of this functor consists of representable presheaves, and by definition of the category, there's a map of presheaves. There's a map of presheaves sending C, which is one of these arrows. Almost got it. there's a functor from these diagrams to, wait, what is C hat? Is a presheaf. So it should be the presheaf. Okay, to a map of presheaves, or phi of C. It's a map. Right. That commutes with the diagrams. This is a map from the colimit of representable presheaves to F, and the claim that this is an isomorphism. But by Yoneda, if X is in C, if X is an object of C, and alpha is an element of X, then there is a map. Then there is a map of from HX into F determined by alpha such that the identity in HXX is sent to alpha. And it follows we can hit any element in any part of the presheaf by a representable presheaf. Okay, I'm a little foggy on that last part, but I'm going to come back to his document. It makes sense here. Simplicial sets would be like chain complexes over F1. You mean the field with one element? Now you're speaking my language. The idea is that a category enriched in chain complexes is hence enriched in non-negatively graded ones. Yeah. My voice sounds strained? Probably it is. Yeah, what's for lunch? Well, let me go fill up my water and grab a banana. Actually, maybe I should have some tea. Actually, maybe I'll grab... okay. I'll have some tea in a bit, but let me grab a protein shake and a banana. Yeah. And then we'll see. By the way, Leo, still no replies on my question, it seems. Still no replies on my question, it seems. Okay, I'll be back in a second. Yes, a field with one element. If chain complexes of abelian groups are simplicial abelian groups, then you could say chain complexes of F1 are simplicial sets, since vector spaces over S1 are sets. Oh. I like this. Okay. BRB. Okay, gang, what's happening? Never distract him by writing in chat. Yeah. I wish I understood genus 3 surfaces. Why don't you take the singular simplicial set realization of the genus 3 thing? Okay. Where are we? What are we doing? Oh yeah, we're looking at this random DoldCon PDF. Geometric realization. Put up the video today. That's probably why some people think F1 should be related to the sphere spectrum. Interesting. That's another thing I need to understand one day. Okay, wait a second. Simplicial abelian groups, right. A is a simplicial object in the category of abelian groups. I would have thought it was an abelian group object in the category of simplicial complexes. I mean, shouldn't it basically be a simplicial complex that lands in abelian groups instead of just in set? Yeah. It means that there's abelian groups and HOMs for each of these, yeah. 3 different complexes. Following 1. Wait, what reference is 1? Simplicial homotopy theory. Okay. So the Moore complex, in which the boundary map is the alternating map of these things, the alternating sum of the face maps. The simplicial identities easily imply that this is in fact a chain complex. Thus, wait a second. Right. That to that defines a functor from simplicial abelian groups to chain complexes. Smash with the sphere spectrum should be the stable version of pullback with F1. Hey, Woodrow John. Is this Akil's PDF? I don't know. Some random PDF I downloaded a long time ago. I have no idea who this is from. But trying to read some DoldCon now. The singular chain complex of a topological space can be obtained by taking the Moore complex, right? Where we take the free abelian group on here. Note that applying Z turns a simplicial set into a simplicial abelian group. Recall that if X is a simplicial set, then a simplex is degenerate if it's in the image of a degeneracy map. This is Akil's notes. Okay. So for a simplicial group, there is a subcomplex of the Moore complex consisting of sums of degenerate simplices of degree n. Okay. And then definition 3, consequently, we can form the quotient complex. Right. If I don't drink this fast enough, it's all sticking to the bottom. Un momento. Okay. If A is a simplicial abelian group, then we define the normalized complex as follows. In dimension n, this consists of the subgroup that is killed by the face maps. Okay. So it's a bunch of kernels. Right, and D is generated by the face maps. Or the DA complex is generated by the face maps, right? It needs to be checked that we have a chain complex. But it is. Thus, we have 3 different ways of obtaining a complex from A. By the way we define the normalized chain complex, we have natural morphisms here. And our goal is to prove that the functor sending A to the normalized complex defines an equivalence of categories between chain complexes of abelian groups and simplicial abelian groups. Right. And n star A. From chain complexes of abelian groups to simplicial abelian groups. Moreover, the 3 complexes are all naturally homotopically equivalent, and the first and last are even isomorphic. Barrett-Pretty-Quillen theorem, which basically says that the K-theory of finite sets, also known as vector spaces over F1, is the sphere spectrum. Actually, I might look that up. That sounds cool. I won't get distracted right now, but I will put it in a new tab here. Equivalence between K-theory and finite sets is the sphere spectrum. Yeah. Wow. Where do I read more? Oh, I guess I could start at the Wikipedia page. Crazy. I'm scared already. This scares me. We don't do K-theory here. Yeah. Okay. Right. Okay. And somehow, so I know that we leverage this to try and form the infinity category version of a derived category in general, of an abelian category. Because an abelian category should be enriched. An abelian category is enriched in abelian groups. And so somehow we use that when we look at we go to our chain complexes, and somehow we use that. We apply the Dold-Kahn correspondence to get a simplically enriched category. And somehow this should be, so that's an infinity category. And its homotopy category should be the derived category. Something like this, right? Yeah. Entirely from this chain complex. Okay, this is the backwards map. A normalized chain complex of a simplicial abelian group looks a lot different from A dot, because a priori has much more structure. Functorial, so we sum over the direct sum of all of these things should recover an. Here the map from a factor of the normalized complex corresponding to some phi from n to k is given by pulling back by phi. Okay. But let's assume that 14 is true. Okay, let's assume that 14 is true. Let's now determine how simplicial maps will play with the decomposition. Here. How simplicial maps will play with the decomposition. Right, okay, we're just writing equality now. Given this map and a factor nak of an for some epimorphism n onto k, we want to know where f star takes this into this. Okay. I'm running out of computing power here, guys. Gotta speak more from the diaphragm. Yeah, okay. Motivated by this, let's describe the inverse construction. If we have a chain complex, we define a simplicial abelian group such that the n chains is this direct sum. Overall the surjections. We can make it into a simplicial abelian group using the above recipe. There's a bit of a subtlety. Just download more WAM. Yeah, I weed more WAM. I weed more WAM. Yeah, I don't have the capacity for subtlety right now. Okay, what's the point? The point is point is what? I guess we do want this map, right? The functor from simplicial abelian groups to chain complexes. Right. Barrett-Pretty theorem. Okay. How are we doing for streamers? Are we petering out in the late hours of the day? We are. We're slowly dipping. Don't worry about this proof. You don't remember the proof and you work in this area. Okay. Works well when tired/unthoughtful. Yeah. Perhaps. Wow, look how short my hair is in that one. Yeah. So, what do I want to go to now? Okay. Dold con, shuffle product. Let's go back to 2.5. In fact, let's go back to chapter 2. In fact, let's go back to part 1. What you're working on by now? Well, we're just looking at Dold Con, the Dold Con correspondence. Now I think what do I want to go to next? Arad gets here just as you're about to leave. Tag team. Someone's got to babysit me. Chapter 1, chapter 2. Yeah. Well, do we dive more into the application side? Do we try and go understand something like QCO? I do confuse both. There's too much blue, I just see blue. I just see a stream of blue in live chat, and I get extremely confused. Okay, I want to keep this tab open and this tab open. Well, while you're both here, let's see if we got a response yet on my post. Still no reply on Stack Exchange. Uh, feel everything I touch this stream will make me sick for the rest of my life. Yeah, it's too late. First chapter of HTT. I'm not gonna watch Gates Gory interview with Kazdan. I did that yesterday. Yeah, let's do QCO. But is QCO touched in HTT? Let's see. What should I look up? Categorical. You know, QCO on bun G introduction. How about learn K theory? No, this is infinity category time. Introduction to stacks and bun G. I don't think that's the one we want. HTT chapter 1 unstable categories. Oh, maybe we do need to look at a modern introduction to algebraic stacks. But yeah, maybe we do need to understand stable categories. Okay. Higher topos theory. Higher topos theory. I have the hard copy here. Right over here. Signed hard copy, by the way. Signed hard copy right over here. Ideal cons notes? Okay, so maybe we will look at those. Yeah, where's the stable stuff? Why is the weather outside like Canada right now? Is because you're spending too much time with me on stream. That's exactly why. Oh no, are you saying oh no because we opened up Lurie? Okay, modern introduction to algebraic stacks, yeah. Okay, let's go through these. A stack of quasi-coherent sheaves, yeah. What are the prerequisites for learning elliptic curves? Well, very little. If you want to learn them at a basic level, you could look at start with Silverman and Tate's rational points on elliptic curves. If you want to go read Silverman's arithmetic of elliptic curves, you maybe want to know a little bit about algebraic varieties going in. But actually, part of me feels like it's not a bad place to learn some things about algebraic varieties. Yeah. Higher topos theory doesn't do stable categories. Higher algebra does stable categories. Right. Gates-Gorey, Rosenblum. That's a very long book, is it not? I was about to say maybe we should go to Gates-Gorey, Rosenblum. Yeah. But let's just do let's start here. Depending on what level, you could do it with just like high school geometry. Yeah, exactly. Given an algebraic variety, well, where are we going? Right, we're talking about moduli spaces. Wow, why does it keep jumping? I think I'm hitting it with my arm. So do we want to go to do we jump right over to stack of quasi-coherent sheaves? Given a scheme, quasi-coherent sheaves form a category, and we've got an adjoint pair of functors. The left adjoint is inverse image, and the right is that. Note that for compatible functors, we have an invertible natural transformation. Together with this extra piece of data, the above diagram does determine a commutative diagram in the category groupoid. It does? Why is it a groupoid? I mean, this is an isomorphism, right? So I guess that's what makes it a groupoid. Everything's an isomorphism. Yeah. The way your elliptic curves, prof, put it is that elliptic curves are the simplest non-trivial example of a lot of things. In particular, the assignment x to qco cannot be assembled into a functor into the one category of categories, right, but only assembled into a functor into the 2-1 category, or equivalently the infinity category of categories. Still, a precise construction of this functor requires more than just the data of an invertible natural transformation. But it gets messy if we try and track too many things. Okay. Let E to C be a functor of categories. F from C to D be a morphism. Maybe I'll say goodbye to Larry's giant PDF. And we might go to Gates-Gorey Rosenblum after this. We're talking about right, fibered categories, basically. Because you're a very sleepy, deepy guy. I believe in you, Leo Lectures. If I'm still at it, you can get at it. Time to stretch, actually. We're more than halfway. This is starting to take its toll on my throat, though, I will be honest. Probably sounds that way, too. Right. But we're basically just talking about fibered categories. So, right. So, E over pi is Cartesian. It's Cartesian if every arrow can be lifted. There exists a lift of this arrow. Yeah. And there's a universal property as well, right? Shouldn't it be something like such that for every map into here or something? There's I think a missing part of a universal property. Eat the content. Yeah. Refuses to react to a video. To which video? I mean, I don't want to react to the interview video, which I already watched yesterday. Maybe tomorrow I'll react to a video, but today's all about infinity categories. So QCO scheme will denote the category of pairs where X is a scheme and F is in QCO. A morphism is a morphism from X to X prime together with a morphism between the pullbacks in QCO, or the pullback in that thing. And given two morphisms, the composite is defined there. And so this is a fibration over schemes. Yeah. And likewise, we could do like modules over our modules, right? In an entirely similar fashion. Yeah. So, let's see, be a category. We denote by cart C the 2-1 category whose objects are Cartesian fibrations. With one morphisms are given by that and are compatible with pi and pi prime, and whose two morphisms are invertible natural transformations. Okay. So Grothendieck says, this is the Grothendieck construction. Grothendieck says that the category of functors, the infinity category, Grothendieck says that the infinity category of functors from C-op into the category of categories, the infinity category of categories, into Cartesian fibered categories over C, he says that there's an equivalence. Haven't you heard you read infinity categories? This sounds less scary now. Wow. I'm surprised this made it seem less scary. Given oh man. I'm getting tired of staring at the screen, I'll be honest. Given that we have a functor from here, the corresponding Cartesian fibration called the unstraightening of F. The Cartesian fibration is called the unstraightening of F. Given a Cartesian fibration, the straightening of pi is the essentially unique presheaf of categories. Okay, who's unstraightening his pi? Okay. Lurie proved a generalization of this where C is allowed to be an infinity category and cat is replaced by the infinity category of infinity categories. Okay. But this gives me no sense of what this unstraightening is supposed to look like, right? So QCO. So QCO is we take QCO scheme. We take this fibered category and we obtain the corresponding functor from scheme up to cat. And then QCO QCO Simic will then be a presheaf of groupoids under what the... Oh, yeah, I guess it's just a presheaf. But then we want to, like, sheafify with respect to, like, a Grothendieck topology, right? You know, it's actually not a... if you look at a Char's book, well... For Baby's first derived category, maybe look at the last couple chapters of Alufi's book. And then for a nice, concise overview, I would actually look at the appendix to a Char's book on perverse sheaves. Cat infinity equals infinity cat of small infinity categories, yeah. Make the PDF into dark background? Oh, yeah. Okay, good luck recording, Leo. How do I go dark mode? Where is it? All tools. Where's dark mode? What about beast mode and goblin mode? Somewhere in my settings, right? It's already a sheaf with respect to a tau topology. Oh yeah, well, that's something because of like. Oh yeah, here we go. Thanks, Ken. Oh, that didn't do any. That just changed the thing around it. Whatever. This is whatever. I think there's like a dark mode setting. Don't I have dark mode here? I don't have a dark mode here. Extensions. Yeah, whatever. It's not that important. I'm not. It's too much work. I'm not gonna bother with it. Sorry, I'm not gonna bother with it. I've lived my life in too much darkness. It's time. It's time to face the light. Oh, here we go. The theorem was facing me right there. Presheaf of category satisfies a tiled descent. Okay. Worst dark mode ever. Yeah. Right. I'm tempted to go look up QCO, descent for quasi-coherent sheaves, but actually, let's stay focused. Let's stay focused on getting back towards the infinity category stuff. What's exactly big picture of descent? Basically, you want to know when you can, when you can pull back sheaves. You can take a pullback of a sheaf along some morphism, and I guess you want to know which way is it. I mean, descent tries to sort of push you forward the other way. I guess you want to know if you have a sheaf on X, you want to know if it came from the pullback of a sheaf on Y, basically. That's my rough understanding. Descent for QCO sheaves just says you can glue sheaves essentially. Yeah. Like I think descent for vector bundles, for example, can tell you, if you want to take a vector bundle on X and push it forward to the quotient. It basically, like, one of the applications is it tells you how that all works. Okay. So in particular, it's a stack, right? Because it's sheafy. The functor from categories to groupoids, sending C to that thing preserves limits. Okay. Given a co-simplicial diagram in an infinity category, a co-simplicial diagram in an infinity, C is an infinity category, and delta is also an infinity category. Okay. Descent criterion? Wow. This all seems very confusing. Okay, maybe this is something good to learn, but I mean, this is just about proving the descent, right? Okay, quasi-coherent sheaves on stacks. Since the full category of affine schemes is a basis with respect to the Zariski topology, we have, okay, I guess we wanted those other theorems to reduce to basis. So the presheaf of categories is a right con extension. Ugh. I don't know what that means. But okay. Okay, for every scheme, there's a canonical equivalence of categories from QCO to the limit over all pairs where R is a ring and X is an R point. It'd be cool to sketch some geometric intuition for all of this. Well, I think the point is exactly, I mean, what is, right? Like, the category of R modules is equivalent to quasi-coherent sheaves, or wait, what am I writing? QCO of this is equivalent to the category of modules over R. Why is that? You take a sheaf over spec R, and you send it to its global sections, right? And that's the equivalence. And how do you go backwards? Well, now someone correct me here. I'm probably going to say something wrong, but to go backwards, you take an R module, and then for every element of your ring, right, you form the basic open set associated to that element. And you, on this is a topological space unto itself, and so you localize your module at that element, and you take the constant sheaf on there. And then, am I right about that? It's not is it? Am I right about that, gang? And then on all the intersections, you basically take you basically use the fact that if you localize by G and then F, or by F then G, you should get some isomorphism. And so basically you locally define what is a quasi-coherent sheaf. Locally it looks like modules is the point. And so you could just glue things that locally look like modules together. You just glue things that locally look like modules together, and that's how you get all your quasi-coherent sheaves. Well, and then more generally for an arbitrary scheme, right? Okay, this isn't the actual definition, but more generally an arbitrary scheme is what? I mean, it's covered by open sets where that open set looks like spec of some ring. And so roughly speaking, if you have some cover of X, what is a quasi-coherent sheaf? Somehow it should be, for each element of your cover, for each ring, it should somehow be a choice of module over that ring, and then you glue them together. Roughly. Yeah. And that's the point here. So, but now let's see. Hang on. Right. So now to define QCO of a stack. Do I draw a weird X? Or maybe like that, I don't know. Right? We want to look at it's over all pairs where x is an R point of the stack. And what does that mean exactly? Well, this is a stack. This is a map from schemes to groupoids. No. Into categories. But I mean it should be fibered in groupoids. It should be fibered in groupoids, right? It should be fibered in groupoids. So it lands, what am I doing? Right. So then, okay. Okay, I guess this makes sense enough. So more precisely, QCO is a functor from the contravariant functor from the category of stacks to the category of categories, which can be defined as the right con extension of the presheaf that sends spec R to mod R along the inclusion. I don't understand how this is an infinity category, but okay. Yeah. Okay, 101. I think I do need some tea and to hit another bathroom break, so I'll be right back. Okay, water's boiling. Is it spelling out Grothendieck's theorem? Is it? Which Grothendieck's theorem? So by definition, a quasi-coherent sheaf on a stack amounts to, for every ring and every R point, an R module, f of x. And for every morphism and pairs of points, for every morphism sending x to x, there should be an R module isomorphism along extending scalars. just follows from the standard tensor product of R and its R module, which is R itself. No, this is, are you talking about this? This is extension of scalars. Because remember, like, right, if I've got like, okay, if I have a ring, so here I have a pair of ring homomorphisms. So then I get a map from spec, I get a map going the other way from spec R prime to spec R. And then, so, like, correspondingly, you got to think, well, how do I get a map? How do I get a map? Actually, why shouldn't this just be pullback? Wait, why are we doing, wait, R points? Right. Oh, but X should be contravariant. Or, I mean, it's contravariant on schemes, but it's covariant on rings. Right. So we should get a map going this way. We should get a map going this way. And so, like, somehow we should map the corresponding modules to each other, right? But fx and fx prime, you can't compare these things, right? They don't make sense because this is an R module and this is an R prime module. So you can't really compare these things, right? But what you can do is you could tensor this over this morphism, and now you could say that they're isomorphic in some compatible way, which is exactly this cocycle condition that we want. Yeah. Okay. Ooh, quotient stacks. Yeah, so we've only got a little under 3 hours left to go. So reminder to everyone, this is a charity fundraiser live stream for Children's Hospital and research. So please donate something, anything if you can. Or if you know someone who can donate, why don't you bully them to come jump on stream and make a donation? Let's go see any response to my Stack Exchange post. No. No response yet. Okay. As discussed in section 0, which we skipped, a G action on a set can be encoded by this diagram where two rightward arrows are the action map and the projection. A G action of a set. Right. The colimit of this diagram is the set theoretic quotient. The colimit over what? I'm very confused. But if we instead take the colimit in the infinity category groupoids, yeah, what is a colimit over? I don't understand how this is indexed, but okay. We get the quotient groupoid. Then we may recover the above diagram by taking the fiber product of the canonical functor along itself in groupoids. Yeah, I'll be honest. I don't understand anything I just read. X will be denote the geometric realization, which is to say the colimit taken in infinity groupoids. Okay. Then we recover the above diagram as a check nerve of the quotient map. This leads to a bijective correspondence. What notes are these? I don't. These are cons notes. My water's probably boiled for tea. Okay. Groupoid objects and effective morphisms. The understanding is slipping away from me. We could go look at Gates-Gorey-Rosenblum. Is that going to make our life easier? You'll never see quotient spaces the way you did in your algebra class again? Yeah, probably not. Probably not. Your mind has been tainted now. Maybe we should keep this open, but let's go. Let's go. But do we want to look at book 1 or book 2? Or do we want to look at something, volume 1 or volume 2? What do we even look at it? Let's look at the preface. Quasi-coherent sheaves on pre-stacks. That's maybe where we want to go. The birth of Indco. Maybe we should just read this whole thing. The main underlying theme of this book is the notion of incoherent sheaf, or rather categories of such on various geometric objects. The most basic way of how one embeds representation theory into algebraic geometry is to look at rep G. We can interpret rep G as the category of quasi-coherent sheaves on the classifying stack. The advantage's point of view is that many natural constructions associated with the category of representations are already contained in quasi-coherent sheaves. Right. The reason is that explicit constructions involve explicit formulas, and once we move to the world of higher categories, we'll be in trouble. Universal enveloping algebra, Why should one mess with algebraic geometry if all we want is a category of modules over an associative algebra? Right. So what about the restriction functor? One can consider the associated formal group denoted by xg, and show this. Okay. One can reasonably get somewhat uneasy from the suggestion to consider the category of quasi-coherent sheaves, but it's a legitimate operation. The functor of restriction still corresponds to pullback. The natural functor in the opposite direction should be induction. Being a left adjoint, it cannot correspond to direct image. Whatever the functor of direct image is, it is the right adjoint of pullback. Okay, I don't really get it. On a scale of e to pi, how tired am I from the mega stream? I don't know. E plus pi divided by, no, e plus pi divided by 2? That's not true. I'm probably more tired. It's actually not that bad, to be honest. You know, people have 8-hour jobs where they sit in front of a computer, but maybe they're not talking nonstop the whole time and thinking intently about infinity categories. You know, like in the grand scheme of things, I used to work overtime at restaurants, and that's not even close to being the hardest job in the world. Did I gain more respect towards streamers? No. I had none, and I've gained none. Yeah. I mean, whatever. It's not easy to be entertaining and to talk for 8 hours and be entertaining. Granted, but oh well. There's plenty of things that aren't easy that I don't know. Whatever. Okay, so what is the problem here? I don't understand the problem. So we have a homomorphism from G prime to G. Restriction still corresponds to pullback along the morphism. Okay. But if we want to talk about representations of Lie algebras, the natural functor in the opposite direction is induction, the left adjoint to restriction. And being a left adjoint, it can't correspond to direct image. Okay. Yeah, I still don't get it, but okay. What happens is that although we can interpret Gmod as this, a more natural interpretation is indco of this, where indco will be explained. It just so happens for a classical Lie algebra, the categories are equivalent. Now, the functor of restriction along the homomorphism alpha. Since I worked in restaurants, my wiki will be similar to Yitang Zhang. Yeah, I mean, if I ever prove anything half as interesting. Yeah. Now the functor of restriction along the homomorphism alpha will be given by this functor, which is why we want inco. Okay. However, the functor of induction will be the functor inco direct image, which is the left adjoint. Okay. QCO behaves more like functions on a space, while INCO behaves more like measures on a space. Okay. What can we do with incoherent sheaves? The kind of objects we want to consider on INCO are a bit more general than usual players. We consider quasi-coherent sheaves. Inf schemes. Okay. Have we strayed too far from infinity category? I mean, this is supposed to be infinity categories. Oh, maybe this is why. Okay, here's okay. It's what we mean by limit. Okay, we should read some of this. No idea what the Durham stack is, but is this theory covered in the legendary notes by Dudonnet? I don't think so. I think this is too modern. This is stream becoming wilder each time you come back. Well, good. Gotta up the ante to keep people donating, keep charitable donations coming in. Although, to be honest, we haven't had any for a while. We've been hemorrhaging listeners and losing donations. Not losing donations, but not getting as many. But I mean, how do we construct the theory of INCO? Whatever inf schemes are, for one such, the category of INCO is bootstrapped from the corresponding categories of schemes by taking a limit. And I guess the limit is why we want infinity categories. Infinity categories applied on mathematical oncology, yeah. Well, what I should be doing is like live streaming, like, solving linear algebra problems for 8 hours. That's what I should have done. You know, calculus review sections for people writing their finals or something. If we literally took the limit in categories of categories, we'd obtain utter nonsense. This is a familiar phenomenon. Literally understood. Limit of, say, triangulated categories are not well behaved. A well-known example of this is the derived category of sheaves on a space cannot be recovered from the corresponding categories on an open cover. However, this can be remedied if instead of the triangulated categories we consider their higher categorical enrichments. So we actually mean a limit of infinity categories, and these are infinity categories. In our case, they have a bit more structure. They're k-linear over a fixed ground field. So we actually have DG categories, which we've seen a little bit. Yeah. Solving Hartshorne problems for 8 hours. Yeah, that could be good. Yeah. For that end, before we proceed further, we need to explain what the DG category for INCO is. For a scheme, INCO will nearly be the same as QCO, yet they are different. The former is obtained from the latter by a renormalization procedure. Keeping in mind our previous examples, we want for every scheme, INCO should contain infinite direct sums. Sure. And for every map, This should preserve infinite direct sums. Okay. This means that the functor takes values. The functor 2.3 takes values in the subcategory of dgcat, where we allow objects only dg categories. Okay. The Dennis Gatesgory category. I guess so. Let's first try to make this work with the usual QCO. The DG category is introduced for an arbitrary pre-stack, chapter 1.3. DG QCO is introduced for an arbitrary pre-stack, and in particular scheme. However, or whatever the DG category is, its homotopy category is the usual bounded derived category. Okay, so chapter 1.3. That's what I really want to understand. That's where we really want to go. Yeah. Sorry, that's probably annoying right in the microphone. Okay, I think this is enough of this. And we're ready to go on. Jump ahead a bit. Fat points again? Yes, I think so. Okay. What is derived algebraic geometry about? What is done in this chapter? Right. Yeah, okay. Not so much about geometric objects, the most general of which are pre-stacks, but quasi-coherent sheaves on these geometric objects. Having at our disposal the theory of infinity categories, the definition of the category of quasi-coherent sheaves on a pre-stack. Should you public the video now or later? Make it public as soon as my stream ends, and then you can funnel people from my stream to your video. Hope you come up with the Kristaps category related to Kasdan-Lustig. Yeah, maybe. I have much less lofty goals at this point in time. Having at our disposal, the theory of infinity categories, the definition of quasi-coherent sheaves, is pretty simple. If our pre-stack is an affine scheme, then this is the DG category of A modules. Okay. So DG category, this means... A mod, what does that mean? The DG cat. Okay, so we actually have to go back further, I think. Or this is just the introduction. Hang on. Yeah, maybe there's something else about DG categories we should be reading. Introduction to part 1, some higher algebra, basics of algebraic geometry. Okay, 1.1 and 1.2. Stable infinity categories. Okay, we should at least read the first part of this. Oh, and DG categories are at the end. At this point, I should put a pillow on my chair. What? Why infinity one categories for reasons, I guess. The limit of a diagram of infinity categories, and the example is gluing. Below we explain why just the above operation of gluing along an open cover unavoidably appears in the theory that we are trying to build. However, taking that on faith, we arrive at the necessity of infinity categories. It is well known that triangulated categories do not glue well. There is no known way to define the G-equivariant derived category of sheaves on X while only using the derived category of sheaves as input. All existing definitions appeal to constructions that take place at the chain level. But once we put ourselves in the context of infinity categories, everything works as expected. For example, given a pre-stack, so an arbitrary functor from affine schemes to infinity groupoids, one can define the category of sheaves on the stack as the limit. So why is it that we can take limits of infinity categories? I mean, is it because we can take limits in sets? And these are set-valued functors, ultimately? Why is it? Your first algebraic geometry class was taught by Gatesgory, and it almost took the whole semester to define Pn. Wow. Interesting. By Pn, do you mean the stack of something, something, something? Yeah. As a tiny particular case, if y is x over g, we recover the g equivariant derived category. We now explain the intrinsic reason why one is often forced to work with infinity categories. Nearly every cat we can take limits in sets. Yeah. Maybe, what if I just ask this question to Google? Why do limits exist for infinity categories? These structures provide an appropriate up to homotopy, too rigid. Okay. Yeah, okay. It was tough, but basically all of your category theory was learned in that class. Although you didn't do a bunch of category theory, you feel you're decent at it. Well, that's good. Has to do with the taking a limit. Basic example of limit is the operation of fiber products. When working in a triangulated category, we want to interpret the latter as the shifted one cone of this map. Why do we want to do that? And arrive to the familiar problem that cones are not well defined. Okay. Of course, we can say they exist, even though they're not canonical. But this non-canonicity prevents one from defining more general homotopy colimits, which are geometric realizations of simplicial objects. And without that, one cannot really do algebra of the kind that we'll be doing in part 4. Okay. Okay. He also brought pizza to office hours once, and nobody had any. So you had to take them to your dorm. Sounds great. Why would no one have any pizzas? People are all worried about their health. I mean, that's understandable. I don't know. Still, free food as a student. It's still a mystery how curves embed into projective space and how you can recover the curve. Is it a mystery? Oh, you can't have gluten. Oh. Hello, Chilled Vibes 99. Welcome to the stream. Welcome to the marathon stream. Okay. When all schemes are fine, apply this here. Wait, what? Let's go back. Consider the pattern of base change for the derived category of quasi-coherent sheaves. Say we have a Cartesian diagram. Then we have isomorphisms of functors. One obtains an adjunction. By adjunction, a natural transformation here. The base change theorem says that this is an isomorphism. The only problem is that this theorem is false. Okay. If x1 is taken to be the fiber product in the category of usual schemes, consider the case when all schemes are affine, and apply this to here. We obtain the map where the tensor product is the derived tensor product. Yeah, I still don't get what is going on here. Hello, Deep Doc Proletarian Archive. Yes, this is very complicated, I would say. This is an alien language. Absolutely. Okay. I still don't understand what the problem is, but okay, we want to replace this with DG algebras. Spectrum of such a thing is, by definition, an affine derived scheme. Okay, so affine derived schemes are necessary if we wish to have base change and if we want to do algebraic geometry. Okay. However, whatever they are, they're glued from these things. And we try to imagine what QCO should be. Should be obtained by gluing these things, some limit of the diagram. Thus, we run into the problem of taking the limit of a diagram of categories. As we said before, in order to take this limit, we should understand the above diagram as one of infinity categories. I still don't understand why. Okay. Stable infinity categories. The main body of this book, we'll be doing DG categories. One would be to proceed directly by working with ordinary categories enriched over the category of complexes of vector spaces. In fact, this way of approaching DG categories has been realized. However, one of the essential ingredients of a functioning theory is that the totality of DG categories should itself be endowed with a structure of an infinity category in order to be able to take limits. But since the paper Okay, maybe this is part of why we have the solution, because I see. So taking limits of general categories doesn't necessarily make sense. But if all of those categories itself fits into an infinity category, we can take limits in infinity categories. So if we form like an infinity category of DG categories, then we can take a limit of DG categories. Yeah, this is definitely PhD level stuff. Right. The situation with the tensor product is similar. Okay. So actually, let me go back a second. Let me go all the way back to this book for a moment. And let's go see. I guess they say something about limits, right? Limits in infinity categories are nice. Certainly this book must say something about it. Let's just read briefly. We'll discuss initial terminal. And this is what they were saying before, right? Is that the approach is that somehow we do this by viewing limits as like initial and terminal objects. I see. An object in an infinity category is said to be initial if for all objects y, the mapping space is contractible. Okay, there's a lot of definitions we're missing now at this point. And I think if we jump over to section 4, so I have Yoneda for infinity categories. And if we jump over to 4.4, in a moment. Let's see. Oh, co-final and co-initial. Wait, what am I doing? This wasn't where I wanted to go. Do we have a table of contents here? Oh yeah, what am I doing? 4.3 is limits and co-limits. Okay. In this section, we give a definition of co-limits of diagrams in infinity categories. And related to the usual notion. Right, in terms of slice categories. We'll prove that if they exist, they're unique up to a contractible space of choices and show that an infinity category admits all small co-limits if and only if it admits small co-products and pullbacks, respectively pushouts. Afterwards, we'll use these findings to indicate how one can show that the infinity category of spaces and infinity category of infinity categories have all small limits and co-limits. Okay. I love math too, chilled vibes. I love math too, as you can tell. I wouldn't be doing this 8-hour stream if I didn't love it. Okay. How's that different from standard categories? Well, I don't think is a category of category closed under small limits, or yeah, it says it's complete and co-complete. We prove that if colimits exist, Oh, but I guess yeah, okay. I don't. I guess it holds more generally. I don't know. Maybe we don't care enough about the one category of categories. I don't know. I don't know. Okay. The definition of stable infinity categories given in Lurie has a huge advantage. Being stable is not an additional piece of structure but a property. As a consequence, we do not have to labor to express the fact that any stable infinity category is enriched over the infinity category of spectra. Okie dokie. Given an unstable infinity category, one can talk about T-structures on it. We count on the reader's familiarity with this notion. And a stable category is the same as the T-structure on the associated triangulated category. Okay. The symmetric monoidal structure on the one category. Okay, you lost me. You lost me. Okay. We have some basics of infinity categories here. Not really familiar with it. Well, just pretend you are. Just pretend you are. If this is an isomorphism in spaces, yeah. What is SP? Let's. No, nothing. Okay. SPCS, probably because it's notation. Well, if you don't even know what a category is, this is probably very alien language to you. This is probably extremely alien language to you. It's just a collection of stuff. It's just a collection of stuff. Objects and how to map between objects. Straightening is also known as a growth and deconstruction. So is that all that is from what the other document was talking about? Right. A fibration of ordinary categories is equivalent to the datum. Right. So it's like a functor from C-op to the category of categories. Isn't it a pseudo functor though? Or maybe that's because we're viewing it as like the two category of categories. Okay. Good. Now you can learn infinity categories without contaminating your mind with the one truncated nonsense. Just the goats construction, yeah. Okay. We have a Yoneda lemma. Probably I should be reading this, right? Okay, here's maybe what we want. In this, we'll assume that we know what infinity 1 categories are, as well as the basic rules of syntax for operating with them. But now we need to know the practice. How do we produce new infinity categories? How do we construct functors between them? Of course, there are some cheap answers. For Q1, take a full subcategory. For Q2, composing two existing functors or pass to the adjoint of a given functor. Yeah. Start a diagram of existing ones and take its limit, and start with a given functor and apply the procedure of con extension. These answers entail the next question: how do we calculate limits when we need to? Right. The circle of ideas is the subject of the present section and can be viewed as a user guide to some parts of Luri. Let's say at this point we've convinced ourselves that we should work with Infinity 1 categories. I don't think we're going to get to these tabs. So, Google says the category theory is sometimes called abstract nonsense. Yes. Both by its detractors and its fans. How do we ever construct functors between two given infinity categories? Because we can't specify what it does on objects and morphisms, we need to specify an infinite tail of compatibilities. Rigorously, we'd have to go to the model of Infinity 1 categories given by quasi-categories and specify a map of the underlying simplicial sets, which no one wants to do. Here comes to our rescue. Here comes the operation con extension. Given a functor from D to E and a functor from D to C, we can sometimes canonically construct a functor from C to E. A particular case of this operation leads to the notion of limit/colimit of a functor. We can think of such a functor as a diagram in E parameterized by D. By taking E to be a 1 category, we arrive at the notion of limit of Infinity 1 categories. Okay. Yeah, infinity category is infinity nonsense. Yeah, I know you're not trolling. It actually said that. I know. And I also wasn't trolling when I said that both its fans and detractors call it that. Do you think it's countries where its mathematicians know nothing about infinity categories? Yes, chilled vibe. You've hit upon the most common category theory joke. You can be forgiven since you're new to it. No, probably not, as everyone has the internet these days. But yeah, I mean, probably smaller countries where maybe most people are. Yeah, I mean, there's probably, like, I'm sure in every country there's at least one mathematician that's heard of infinity categories. But I'm sure there's some countries, small countries whose interest is not in, just doesn't have any interest in abstract nonsense. I'm sure there's no mathematicians in those countries have like working knowledge of infinity categories. I'm sure that is the case. Yeah, I'm sure there's a lot of subjects you could cook up examples for that. This is Gatesgory Rosenblum. I should make a community post. Maybe. I think I've already opened and closed, and some of the PDFs I've opened. I don't even know where they're from. TBH. Yeah. Okay, but now we're just jumping right to limits. Okay. Okay. I mean, I'm happy to just accept they exist now, I guess. We've got, the right con extension and the left con extension. And then if we take C to be the single thing, then then we just recover limits and colimits. Am I a student or a teacher? Yes. By which I mean I'm a PhD student, so I'm both. I am both. We record the following piece of terminology. Colimits over the category delta op are called geometric realizations, and limits over the category are called totalizations. Okay. Okay. An infinity category is said to be contractible if the geometric realization is isomorphic to a point. Okay. Suppose we have an infinity category and let this be a functor. Then it follows from this section that there is a canonical equivalence. Yeah, I don't really understand. What is SPC? What SPC? Yeah, it's really not coming up with anything. It's bugging me. I mean, I'm sure it means category of spaces, and maybe that's a... Maybe I should just ignore what that really means. Some generalization of topological spaces. Colimits over delta op and limits over delta, aren't those the same thing? Good question. Good question. I mean, they probably say the word spaces, right? They probably say the word spaces. Doesn't it have some word bib? Maybe. Maybe. Oh. Yeah, we say we let it denote the infinity one category of spaces. What does that mean? The infinity category of spaces is a mathematical structure whose objects are topological spaces or CW complex. Boom, boom, boom. Oh, okay. Formally constructed as a simplicial set with extension properties. Okay. Google said it was the infinity category of spaces, whatever that means. Yeah. Topological spaces, basically. But you think about maps and higher morphisms. Hello, Sir Devio. Hello, Sir Devio. Has anyone noticed how I often say hello twice in a row? I don't know why I do that. It's double welcoming. Okay. Where were we here? Did we lose our little... Where are we here? Okay. Stable infinity categories. Okay. That should be on page 6, which we were well past. Okay, we had basic operations. I'm confused about con extensions. Maybe we should go to limits, colimits, and presentable infinity one categories. Stables on 41. So let's go to 24, and then maybe soon we'll go to 41. Contractible functors. The category of spaces is the homotopy coherent nerve of the category of complexes. Right. Okay. Of complexes. Of the category. So we form the category of complexes. And then, right. We looked at the homotopy coherent nerve a couple hours ago. Did I close Keratin? I guess I closed Keratin. We definitely looked at the homotopy coherent nerve a couple hours ago. I don't remember what it was exactly. But okay. Homotopy coherent nerve. It was something we formed like the path simplicial category attached to a poset category. That was part of it somehow. Yeah. Contents of the subsection can be skipped on the first pass. Okay. I guess. If you say so. Let's go to 42. Stable. Okay. In the section, we study the notion of a stable infinity category. This is the infinity categorical enhancement of a triangulated category. Okay. The main point of difference between these two notions is that stable categories are much better behaved when it comes to operations, such as taking limits. Okay. Related to this is the fact that given a pair of stable categories, we can form their tensor product, discussed in the next section. Okay. In a way parallel to abelian categories, the additive structure carried by infinity 1 categories is in fact not an additional piece of structure, but rather a property. I don't know what that means. Wait, it carries an additive structure? Wait. Wait, what's in it? Okay. Why does it carry an additive structure? I mean, an infinity category is a simplicial set satisfying this horn filling condition. So I don't know where that additive structure is supposed to come from. Okay, 2:02. Time to stretch. Oh, a little under 2 hours left in this marathon. So just another reminder, everyone. This is a charity fundraiser. I'm trying to raise money for Children's Hospital and Research. We were doing good this morning, but wow, most of this time we have not been making any money for the kids. But that's all right. Or is it? Maybe I should be guilting you guys harder into this. Let's see how many people we have streaming. Yeah, I mean they've been showing up in my research more and more, and it definitely is the modern perspective on things. So, probably a good idea for me to learn about them. PDF arg is because of abelian categories. What? Well, it says in a way parallel to abelian categories. But I don't know. Nothing I know about infinity 1 categories. Yeah. Has to do with additive structure so far. But there's yeah, I don't know. Yeah, my research is more grounded in the sense that I'm dealing with like ordinary derived categories on honest to God algebraic varieties. Um, for example, that's something I work with. Meanwhile, the more modern perspective is to be dealing with stacks and infinity categories. Yeah. Okay, so whatever. An infinity category is stable. Oh yeah, right. Sorry, I wanted to go check, see if anyone's answered my question from this morning's argument. No responses yet. 3 upvotes. Viewed 69 times. Nice. Every object is the double loop of its double suspension. So every Hom is a Hom into a double loop space. I don't understand at all. I mean, I can accept that if every object is the double loop of its double suspension, somehow this is a homotopy thing, so it has a abelian group structure, higher homotopy thing, but why is every object the double loop of its double suspension? That I don't know. Where are we here? So we say it's stable if it has fiber products and pushouts. If the map from the initial object to the final object is an isomorphism. Zero object. Diagram is a pullback if and only if it's a pushout. Because those are mutual inverses in a stable infinity category. I don't even know. I mean, what is omega and sigma in a infinity category? I guess is being defined here. So this is the shift by -1. Is omega c, which is the zero object fibered over c, and then sigma c is the push out. Push out? No, this is a pull. No, this is a push out. Over c. Okay. The functors. Okay. So somehow those are shift functors. Okay. Then we consider the homotopy category of C. I'm definitely missing some notation here. But it should have the structure of a triangulated category. Distinguished triangles are images of fiber sequences. Okay. Okay, so whatever. The takeaway is that stable infinity categories have some triangulated structure coming from the zero object. Okay. Lurie tensor product, infinity one category of spectra. Should probably understand that. DG categories. Well, maybe we should definitely understand DG categories. 76. Oh, doesn't it start here on page 76? Maybe it was mislabeled. Duality for modules over rigid categories. Wait a second. DG categories. Here we go. I was just wrong. It's 78. Okay. Throughout this book, we'll be working over a ground field of characteristic 0. To K, we can attach the infinity 1 category of complexes of vector spaces over K. This is the derived infinity category attached to the abelian category of vector spaces in the sense of Lurie. Okay. Last section, change of notation. This is the derived infinity category. Maybe, was this defined in a previous section? It's defined in Lurie. Okay. So this has a T structure, and the corresponding abelian category is the usual abelian category of K vector spaces. It's stable and co-complete. Yeah. The good news, however, is that the derived infinity category... Okay. What if we just try and understand the derived infinity category of vector spaces? The derived infinity category... Let's find a PDF. Hey, K-theory. The universal property of derived infinity. Maybe we should go there. Infinity category talks. Maybe we should go there. K-theory drinking game. Every time I don't understand something, take a drink. You'll die instantly of alcohol poisoning. A user's guide to infinity categories. Okay, let's click on this. Oh, I've been here before. Okay. Maybe we should be clicking on this. Isn't this just one? Actually, maybe this is just part of the book that we're already on. Okay. Let's look at this random other PDF, I guess. Yeah. I mean, maybe this was covered elsewhere, right? The derived category of vector spaces. Why won't it let me see what I'm typing? Let's go here. Let's just search derived cat. Yeah, okay. Maybe we should go back to keratin. I don't know. I'm lost now. I don't even know where I'm going. Recall that a spectrum consists of an infinite sequence of pointed topological spaces, together with homeomorphisms between their the loop spaces. The collection of spectra can be organized into a stable infinity category. Moreover, SP is in some sense the universal example, motivates the terminology. It's stable if it resembles the infinity category, whose homotopy category can be identified with the classical stable homotopy category, which we'll return to. Hello, Onage Effects. Hello. Let A be an abelian category. Under mild hypotheses, we can construct a stable infinity category whose homotopy category can be identified with the drives category. We'll outline this in section 13. Okay. Nice. Maybe this is the document I want to be reading. Yeah. Okay, let's try jumping ahead to 13. If it's too confusing, we go back to the start. This is section 50, page 53. There's a blog called Climbing Mount Bourbaki. I know it well. They have a post about the drive to infinity category. Yeah, maybe we should go there. Let's look at this. We're already here. Consider abelian categories with enough projective objects. We begin by considering an arbitrary additive category. Take chain complexes. The category of chain complexes is naturally enriched over simplicial sets. Right. Complexes are naturally enriched over simplicial sets. Whoa, okay. I didn't know this. This is characterized by the property that for every simplicial set, there is a natural bijection. But maybe we actually saw this already. Well, there's a natural bijection. A tensor C of K? What does that mean? Oh, sorry, this is the chain. Oh, sorry, that's C of K, the normalized chain complex for computing homology of K. Right, so that C and K is a free abelian group. We see that vertices are just maps of chain complexes, and an edge is determined by a vertex corresponding to a chain map, a vertex corresponding to another chain map, and a map which determines a homotopy. What in the seven hells are you looking at? You are looking at the deepest layer of hell, infinity categories. It's very crazy mathematics. That's what you're looking at. Right. The classical Doldcon asserts that chain complexes are equivalent to simplicial abelian groups. As we saw. We extract a mapping complex. Oh, this is going over the Doldcon. Okay, now if A is any additive category, then if this is a push out in the ordinary category of chain complexes, and that F is degree-wise split, Okay. Then the above diagram determines a homotopy push-out square in the infinity category given by the nerve. Okay. And the infinity category of the nerve is stable. Okay. Okay, so the point is, if we have an additive category, the nerve is a stable infinity category. You're curious on its applications? Well, real-world applications are virtually non-existent. Mathematical applications are shows up in like modern algebraic geometry and the Langlands program. Okay. So additive category. Suppose that chain complexes. Let's be the full subcategory stabled under translations and formations of mapping cones. Then this should also be a stable category. And in particular, if it's bounded, is that minus sign is below or above? Right, bounded below. Then this is a stable category, stable subcategory. Okay. So for an abelian category with enough projective objects, we're going to let D minus A denote the nerve of the simplicial category of chain complexes, where A naught is the full subcategory spanned by projective objects. Okay, this is familiar. Okay, so here's a definition. So the derived category of an abelian category A. This is the nerve of the simplicial category of chain complexes. I should make this a minus. Chain complexes bounded below chain complexes of projective objects of A. Okay. And this is it's the simplicial category. Right. Because in general, the simplicial, right. Simplicial, I mean, we've been over this and have forgotten it. The simplicial set, or simplicial category, simplicial category, right, because it's enriched in simplicial sets. Right, and that's its Hom sets. Because the Hom sets, right, the Hom sets of this thing are given by, wait a second. There's the nerve of a simplicial set. But what's the nerve of a simplicial category? I mean, a simplicial category, I feel like we've been over this in Carradine as well. The simplicial category is enriched in simplicial sets. Right? Am I crazy? Two definitions of nerves. The simplicial nerve sees a simplicial category then there's two ways of constructing this. Right. Okay, we have seen this before. The simplicial nerve. It's the homotopy coherent nerve from keratin. Right. Okay. Right. It's the homotopy coherent nerve, which I guess I still don't have my head around, but I kind of get it. Okay. Right. Okay. The homotopy category can be described as follows. Objects are given by bounded above chain complexes of projective objects, and morphisms are given by homotopy classes of chain maps, so consequently it can be identified with the derived category. Yeah, with boundedness conditions imposed. Applications, the construction of the category of rigid motifs, for example. Yeah. Time for a banana. Actually, let's go back to that thing in keratin. Let me move the mic away so you don't get all the mouth sounds of me eating. Let's close some of these tabs. We're not using all of these tabs. Homotopy coherent. 13 watching. Wow, we're really losing numbers now. I don't think we've had a donation in hours as well. The poor kids. Whatever. We've at least received more donations for the kids today than I think we would have if we were working minimum wage. So there's that. Right. The homotopy coherent nerve sent N to HOMS from this path simplicial set. No. From HOMS between these two simplicial categories. Right. Right. Okay. Let A be an abelian category with enough projectives. Then this is stable. Okay. Okay. I think I'm good enough on this for now. I think I'm good enough on this for now. Okay, let's abandon this. Let's go back to where we were in the Gates, Gorey, Rosenblum stuff. Okay. Where were we? Oh man, I can't wait to go outside. Where were we here? You tried donating, you got a receipt, but it doesn't seem to appear in the total. Oh. Well, thank you very much, Ben, for donating. I'm glad you're enjoying the stream. Well, if you got a receipt, that's good. Yeah, I guess maybe the total. Is there somewhere else we can check the total that's been? How else do I check the total? Maybe if I click on the video. Total raised 120. Total raised 120. Yeah, and I think that's USD, which is $5 million Canadian. So, that's not bad. Your bank is tight with security. Yeah, fair. That's a good thing, I would say. That is overall a good thing. Okay, let's see. Okay, so we have our head around the derived infinity category a bit more. What do we want to do? Okay, basic operations with infinity categories. Okay, whatever. We can take limits, stable infinity categories, DG categories. Okay, let's go back to here one more time, and then maybe we can look at the next document and try and understand some sheaves or something. That's exactly 15 times 8 hours. Oh, okay. Yeah, I mean that's Canadian. Well, we've made more because 15 is the minimum wage Canadian, which translates into like $9 American. Still on, hey? Why are you actually learning this? Well, I mean I do have a non-trivial need to learn this. Do I actually have a need to? No, I mean, arguably for the research things I'm working on currently, I don't need to do this. There's other things I should be spending my time on. But this is what people voted for. People voted on YouTube and Twitter, or X. So this is what people voted for. 8 hours, baby. Okay. Okay, so I'm fine. The derived category attached to the Boolean category of vector spaces. Okay. Learn about spinal catastrophism. Okay, I'll look it up. Just for you, I'll look it up. I may look at it later. The secret story in your bones. Is this the one you were telling me about? This long video. Are there people in my department that know this stuff? Yeah, there's one person in my department that knows infinity. Actually, there's maybe a couple. There's maybe a couple who know some infinity categories. Okay. Right. So I'm good. Okay, so vector spaces. One recovers right completion. Okay, there's a universal property of the derived category. I think Mount Bourbaki post talks about that. SPTR, is that Spectra or something? Yeah, I'm still lost on that stuff, but that is the video. Okay, let me click on it at least, and then I will, because I don't like watching ads, even though I make money from ads. I'll go drop it in Brave. I'll save it in Brave, and I'll watch it later in Brave.
This video is brought to you by Trophy Bone Artistry.
The video wants to be watched. Notion of a DG category. The rest of this chapter, we develop modules in one cat over symmetric monoidal categories. If we replace this by any rigid symmetric monoidal category, we denote the full subcategory. DG cat non-complicated maybe. Consisting of those vec fd modules. What does that even mean? What does that even mean? What is a vec fd module? If you tell me in the end, you will tell me if spinal catastrophism or 3 categories or more schizo. Okay. Okay. I mean, 3 categories seem wild. So what is this? Somehow we define an action of finite dimensional vector spaces on another category. Yeah. Okay. Maybe we can go over to basics of derived algebraic geometry now. Why pre-stacks? What do we say about pre-stacks? Okay, let's just read the beginning part of this. Hello again, Adib. Hello. This chapter is meant to introduce the basic objects of study, derived algebraic geometry. What did you miss? Not a lot. Not a lot has happened. I've just been confused about the same things. Hello, stop. Problem is that locally ring space is a lot of structure, so definition's quite heavy. Sure. Now, it is not difficult to characterize which functors correspond to schemes. Essentially, the functor needs to have a Zariski atlas, a notion that has an intrinsic meaning. This is exactly the point of view that we'll adopt in this chapter throughout the book, with the difference that instead classical affine schemes we consider derived affine schemes, which by definition, the category of the latter is the one opposite to the category of connective commutative DG algebras, and henceforth, when we write affine schemes, we mean the derived version and denote the classical one with a CL. And instead of functors with values in the category of sets, we consider the category of functors into infinity groupoids. What are these 2 notes? This is Gates-Gorey Rosenblum. This is Gates-Gorey Rosenblum, chapter 1.2. You promised us the last time you spill your existential crisis on stream, but you feel lost, like in life. Then I don't know. You gotta talk to someone about that. You gotta talk to someone about that. If you feel lost in math, then that's less of a problem. We denote the category of functors by pre-stack and call its objects pre-stacks. A pre-stack is something that has a Grothendieck functor of points attached to it with no further conditions or pieces of structure. Okay. Thus, a pre-stack is the most general kind of space you can have in algebraic geometry. All other kinds of geometric objects that we'll encounter will be pre-stacks that have some particular properties. This includes schemes and all of this other stuff. So we want QCO. You've heard nice things about this book. What do you think? Well, I think it's essential reading. I think it's essential reading for anyone wanting to try and get involved in this stuff, I think. Yeah. Central among these is the assignment to a pre-stack of the category QCO of quasi-coherent sheaves on Y, considered in the next chapter. In fact, there's a canonically defined functor from pre-stacks to DG categories. This is the right con extension of this functor. I guess I should go back and learn con extensions properly. Maybe that's what I'll do with the last hour of my stream, is learn some basic one category stuff that I never learned properly. Yeah. You tried to play pretend mathematician for a semester, doing the coursework, doing the seminars, being a TA, but you just don't feel satisfied. Well, why don't you feel satisfied? What do you need to do? What do you need to do to feel satisfied, to be a real mathematician? We're all just playing. I don't know. We're all just playing. You did get a lung infection, so your exams weren't very well. Damn. But you passed all of them sitting in the hospital and just thinking of what you're even doing. Well, yeah, I don't know. Yeah, I don't know. Maybe, I don't know. Yeah, if math doesn't make you feel satisfied, then... Well, if you're so behind, I mean, whatever. Like, I don't know. People infinitely people much more behind than me have made it. And I feel that I am too far behind to make it. Even though I'm aware of that fact. So I don't know. Think about that, I guess. But it could also be, yeah, maybe math isn't the right thing. I don't know. Maybe math isn't the right thing for me. I don't know. Who knows? Con extensions are cool. There's a Stack Exchange post. Toy examples. Okay. Toy examples of con extensions. Toy examples of con extension. Here we go. Okay, let me read a little more of this introduction though, and then we'll jump over that. Yeah, we take some limit over this. So an object in QCO Y is an assignment for every S, a quasi-coherent sheaf on S, really an S module. And for every morphism, an isomorphism with a pullback between these things, which we've seen before. We talked about this hours ago. And the expression involves taking limit in the infinity category of one categories. Thus, in order to assign meaning to it, we need to input the entire machinery of infinity categories. Right. Yeah. Okay. Because we should really view all the collection of all functors from pre-stacks to DG categories itself as an infinity category. And then we can take limits in infinity categories, I guess. I still don't understand why. It seems like we can take limits in ordinary category, but okay, whatever. We need flexibility for some reason. The definition of the derived category of quasi-coherent sheaves on even such benign objects as algebraic stacks was quite awkward. Essentially, in the past, each time one need to construct a triangulated category, and one had to start from the Boolean category, take its derived category, and do some stuff. As an application of the assignment, we obtained an automatic construction of D modules. Hell yeah, that's what I like to see. Well, D modules, crystals. We define this to be, okay, the DRAM pre-stack. Somehow we need to define that thing. And I remember there's some infinitesimal identification going on. I remember from the lectures. Any advice would be appreciated to find what you're even doing and to get your joy back. Well, I mean, I guess focusing on getting healthy is probably number one priority, which, okay, that's probably meaningless. Of course, you're already doing that, I guess, to some extent. How to get your joy back? Yeah, I don't know. Some people would say step away from math for a bit and try some other non-math things. Yeah, take a break, maybe, some people would say. Maybe you need to spend more time exploring the math that you thought was fun, the math that you enjoyed, that you enjoy doing the most. I don't know. Maybe you're meant to be a neurosurgeon instead. Who knows? These are questions I ask myself. It's now 8 days before your exam, and you just have not studied accordingly. Well, you got 8 days to start studying accordingly. Like, you can still not do a lot of the exam problems without flaws or getting stuck in one shape or another. Does your professor have any office hours before then? Can you get a tutor? Have you reviewed your homework? Do you have graded homework assignments or tests that you can review? Yeah. You had to fight your family to not be a doctor. We're all doctors. Well, fair. Yeah, I don't know. Maybe you just got to do more different math then. I don't know. You don't have office hours where you are? That's weird. Yeah, that's unfortunate. Yeah, Descend's just doing what he can, and if it's not enough, so be it. Yeah, I mean, that's all you can do. Do what you can, and maybe you don't make the cut, and then that sucks, but then you move on. Yeah, that's just how it be. You don't have a way to get a lot of help or feedback. Does your professor not grade your homework or give you example? Yeah, weird. I don't know. Yeah. Okay. So I guess let's go look at con extensions. Then. Background. If C is a co-complete category and F is a functor between small categories, then lan F, then the pullback has a left adjoint called the left con extension. Choosing a math community more than a big name university is essential. You learn this the bad way. I mean, I think if you can factor in as many of these things as possible, it's important. I don't know. big name universities are helpful, but yeah, you want to be in a good community. So f from I to j, we get our pullback functor from ham jc to ham ic. And this is right. And then there's a functor going this way, lan, and lan is the left adjoint of the pullback. One may express it as the following coend. There's one more thing eating away at you is jobs. After your grad school is just eating away at you because pay in India is pretty much non-existent. Well, that also makes life harder. Yeah. It's just equivalent to 300 USD per month, and it's not great in the job market. Yeah. I mean, well, it sounds like I don't mean to say the boat I'm in is comparable to yours, but I'm applying for, I'm in the postdoc application process, and who knows, who knows where things will end up. Yeah. I don't know. Just got to shoot your shot or something, and you're actually planning to go back to your country after saving 200K. Life in the North is overrated. Yeah, fair. You wish you guys could help with these statistic questions and everything? Well, Matthias, can you afford a tutor? Maybe you could get a tutor. Or, there's like Reddit places or Discord places for stats. Probably you could go ask questions. Yeah, co-completes. I forgot. I only read the definition a couple hours ago, and I've read it 500 million times in my life. Something about containing colimits or something, yeah. So it's given by the following coend. What does that even mean? Yeah, I don't even know what that means, though. What are some toy examples of left con extensions? I know that left con extensions are generalizations of colimits. That they're generally useful for constructing pullback functors of presheaves, and the definition of left-derived functors in the context of model categories and homological algebra. But you'd like to see some specific easy examples, which are perhaps not really important, but show what's going on. Here's an example. Consider the inclusion from what? This is the discrete category to this poset category. The left con extension corresponds to the functor. Oh, I see. To the functor taking pairs of objects to morphisms, which maps a pair of objects to the morphism into A plus B. Right. Yeah, I don't have any intuition for this yet either. It kind of makes sense to be the integral. Colimits are like sums, right? Integrals, coends are big sums. Yeah, I mean, that's probably where the intuition's coming from. Oh, Martin Brandenburg. He's always out here asking interesting questions. Oh, here's one you might know. If F from H to G is a group homomorphism, then the pullback between functors into vec is the restriction of group representations, and the left adjoint is the induced representation functor. If G and F are finite, then ind F is also right adjoint. Induced representations can be written down. Wait, what does this have to do? What's the lan F? Does that make it the lan F? What if I type in this? Why do con extensions generalize colimits or limits? Whatever, it doesn't matter. A limit is a specific instance of a left con extension when the base category is the terminal category. Yeah, why don't we just open up... What if we have... surely this is in Real's book. Why don't we... where did... I think I just called it context. Okay, let me go to... here. Exactly, Sergio Polar Bear. Extension problems are pervasive in mathematics. For instance, iterated products of a fixed positive real number, such as 2. The resulting function can be extended to a homomorphism from the additive group of the integers to the multiplicative group. Right. By taking nth roots. Order of a reversing function extending this is a special case of a solution to a categorically defined problem of extending a functor along a different functor, but not necessarily a subcategory inclusion. In general, strict extensions may or may not exist. Obstructions can take several forms. Yeah. Come in dual left and right-handed forms. General definition and some basic examples are introduced in 6.1, which explains... Okay, let's just go over to 6.1. Okay. You want to try and get Real's book signed by her at JMM? That would be cool. Well, you should do it. You think aspiring mathematicians and aspiring artists share many of the same struggles? Yes, absolutely. Absolutely. If j equals star, then f to there's unique functor and lan is the colimit. Yeah, but I want to unpack this. Where do you find tutors? Like literally anywhere. Just Google math tutors. I mean, I tutor, but I can't help you with statistics. But there's online tutors all over the place. Just Google, where do I find math tutors? You can draw the triangle. Well, let me review the definition of con extension here. There's just not as many depictions of math struggle in media or literature, so maybe that's a source of discouragement. Yeah. Well, there is this book. Living Proof, Stories of Resilience Along the Way. You could just go read this book. The best part of one professor he wanted to work under in Riemannian geometry said he wants to be sure if you really are fit to do a PhD in math. And that was kind of the first crack. Yeah. I don't know. I mean, there's two minds about this, right? There's two minds about this. Either you just ignore the people who tell you no, and you do it, and you try to do it anyways, and you either make it, You hear stories about people making it when people said, "Oh, you can't make it," right? Or I don't know, you still don't make it, and that's just the way it goes. But at least you tried, right? Or I don't know, you also just come to an understanding of where your strengths are, and then there's value in knowing when to call it quits. I have no idea. These are two like orthogonal philosophies, and I don't know which one to suggest to you because I don't know which one to take for myself, to be honest. So wish I could be more helpful. Yeah. Okay. Where are we here? So, a left con extension along K is a functor from D to E with a natural transformation from F to the composition such that for any other G from D to E, gamma factors uniquely through as illustrated. So for any other G, gamma is the composition there. Just take you all as my students. We'll gladly do research on KL. Yeah, well, as soon as I get the budget. Also, do you really want me leading you? You may think so, but that could possibly be a terrible idea. Dually, okay, 301. So let me just say 301. We're in the final hour of our marathon live stream. Time to stretch. Reminder one last time, this is supposed to be a charity fundraiser for Children's Hospital and Research Center. So, be much appreciated if you could make a donation for the kids. Whatever you can. And whatever you can donate for the kids. Yeah, I guess that's all. Just wanted to remind you all of that. Let's see if my question from our debate this morning got any responses yet. Still no responses. Lost an upvote. Yeah. Can I improve the clarity of this question? Probably. Yeah. Maybe if I add in, do you think it's helpful if I add in the analogy about finite sets? Maybe I'll add in the analogy. Without the x of infinity, one can still do piano arithmetic. Let's put some respect on his name. However, in order to work with the natural the work with / manipulate the set of all natural numbers, one must add the axiom of infinity. I don't know. Actually, should I even bother? No, I'm not. I'm not going to bother updating this. I'm going to leave it as it was. You prefer to view higher categories through the lens of enriched categories over cat? Okay. The exam on Saturday will all be Markov chains, random variables, etc. Well, you should probably not be hanging out and stream then. You should go be studying. That's what you should be doing. Okay, where are we here? Where are we here? Derived algebraic geometry is born from connective commutative DG algebras in the same way as classical algebraic geometry is here. Following growth in Deek, we'll think of geometric objects as prestacks, arbitrary functors from the infinity category of connective commutative DG algebras to that of spaces. We will think of geometric objects as prestacks, arbitrary functors from the infinity category of D algebras to that of spaces. Consider the stable symmetric monoidal vec and its full monoidal subcategory okay. Because this is in the sense of the chain complexes. By a connective commutative DG algebra over K, we shall mean a commutative algebra object in here. Okay, what is vec at most 0, actually? Maybe that's from the previous document. I mean, we said that vec was the infinity category, which is the homotopy coherent nerve of chain complexes. Right? So what do we do with that? What am I reading about today? I'm reading about infinity categories. Trying to. I'm sure trying. Yeah, I guess this at most n notation. Yeah, it's got to be something to do with that. Okay. Okay. The totality of such algebras forms an infinity 1 category, which we call com-alg vec at most 0. Are infinity categories cooler than homotopy types? I mean, they're very much related. To each other. I mean, in homotopy type theory, one essentially treats all types as like infinity groupoids. You think of everything as an infinity groupoid. So these things are very much connected to each other. You think it's just infinity 1 cats versus infinity 0 cats? If homotopy types are infinity groupoids, right. Yeah, homotopy types, right. So infinity 0 categories, yeah. Yeah. What we call a connective commutative DG algebra over K is really an abstract notion. We're appealing to the general notion of commutative algebra in symmetric monoidal category form. However, one can show that the homotopy category of the infinity category as a familiar object is obtained from the category of what one calls commutative differential graded algebras over K concentrated in negative degree by inverting quasi-isomorphisms. Okay. So the category of derived affine schemes over K is the commutative, is the opposite category of this thing. Okay. So what we call a connective commutative DG algebra. Okay. Okay, what is yeah, vect lec 0. What is this? What is this category? No, that's not what it refers to. The category, boom. Yeah, what do they mean by connective? That's also a good question. Connective commutative DG algebra. Connective commutative DG algebra. What's for dinner? I don't know. I don't know what I'm gonna. I mean, I still have more of what I had for my earlier lunch, of like lentils and rice mixture. Yeah. But I feel like as soon as I'm done, I think I might go. Maybe I'll be too tired or something. But I feel like I need to go for a jog. Get my body moving. I've been sitting in this chair all day, which can't be good for me. Yeah. In this paper, we undertake a basic study. So you're vegan? I've been vegan. I am in my last hour, Raymond. That's true. I've been vegan, but more recently, I've been more just vegetarian, even pescatarian, one might say. Yeah. In this paper, we undertake a basic study on connective commutative differential graded algebras. Okay, where's the definitions? No, this assumes we know the definitions. Okay, differential graded algebra. Maybe we can find the word connective here. No. What is a connective differential graded algebra? It's a type of algebraic structure used in homological algebra, specifically a differential graded algebra that has its mass concentrated in positive degrees. Okay, is that what the connective means? This is just searching the same thing again. Is that all the connective means? Connective. The keys constraint. A DGA is connective if its cohomology vanishes for all positive degrees. Okay. There we go. That's all it means. Okay. By a connective commutative DG algebra over K, we should mean a commutative algebra object in VEC at most 0. So, Boney's saying this is the stable category. Right. I guess it's like we're forming the homotopy coherent nerve for the simplicial. We're forming the homotopy coherent nerve for the simplicial category given by complexes in vector spaces. But I guess we're only considering complexes which are bounded below 0. Yeah. And then the homotopy category of this thing is obtained from commutative differential graded algebras concentrated in degrees, in negative degrees, by inverting quasi-isomorphisms. Okay. So the category of derived affine schemes is the opposite of this thing. A derived pre-stack will be something on there. Right. I.e., the infinity category of pre-stacks is defined to be the category of functors here. Yoneda defines a fully faithful embedding. So maps and pre-stacks between these things. Is the negative dimension of vector spaces related to the idea of the Grothendieck group, where the monoid we start with is the vector spaces indirect sum? I have no idea, to be honest. I have no idea. Sorry, I don't know. I don't know what the point of that is. Yeah. Okay. We say that a morphism is affine schematic if this fiber product is representable by an affine scheme. Oh, it is. Okay. Well, nice guess. Much of the analysis in derived algebraic geometry proceeds by induction on how many negative cohomological degrees we allow our DG algebras to live in. We initiate this discussion in the present subsection. What is this notation now? Is this supposed to be, this is like the intersection of two T structures? Oh, maybe this is supposed to be the corresponding, I see. Right, we take the intersection, so everything above negative n to 0. Okay. This fully faithful embedding admits a left adjoint given by the truncation functor. Right. It is clear if this is a morphism in here such that this is an isomorphism, then what? Then we're all good on tensor products? That's not clear to me, but you remember from browsing NLab on the toilet last year. Yeah. Yeah, virtual representation is one way, but you can also see like you get the integers as the growth and degroup of the category vector spaces, for example, and which basically adds the formal inverses, right? So this implies that this category acquires a uniquely defined symmetric monodal structure, and this functor's symmetric monodal with respect to it, I guess. Okay. In particular, it should induce a fully faithful functor here, whose essential image consists of those objects that belong to there, when regarded as plane objects. So that should also give us a truncation functor on the level of these things. Okay. And we'll say that a scheme, an affine scheme, of course, in the derived sense. We only needed almost 8 hours in going back to the first pages on the book to start cooking DG categories. Yeah. We should say that S is n co-connective. If S is equal to spec A, what? Where's the use of n here? Why does that have anything to do with n? Okay. I think there should be something on n here. Like this part of the definition definitely depends on n. So I guess we'll just take it to be that. I think given M a monoid, then if you've got a morphism to any other group, then that morphism factors through the growth and D group. Yeah, something like that. That's one way to define it with the universal property. Yeah. You can sort of construct it more concretely. Otherwise, like for a category. Well, is that more concrete? I mean, yeah. Co-localization. Okay. I'm getting lost in all of this now. Convergence. I guess that's for the limits. Any pre-stack is convergent. Okay, what does convergent mean? The idea of the notion of convergence is that if we perceive a connective commutative DG algebra is built iteratively by adding lower and lower cohomologies, we can ask whether the value of a given pre-stack on such an algebra to be determined by its values on the above sequence of truncations. It's a necessary condition if we want to approach our pre-stack via deformation theory. Notice that this assignment is naturally a functor from this poset category to affine schemes over S. Okay. Let Y be a stack. We say that the stack is convergent if for each S this map is an isomorphism. Okay. Okay. Okay, we have a notion of finite type. How is deformation theory related to Hecke algebras? I don't really know. I mean, Hecke algebras depend on affine Hecke algebras depend on some parameter Q, and so Well, if q equals 1, then it is... I don't know if it's actually related to deformation theory proper, but if q equals 1, then it just becomes like the group algebra for a Weil group. And so if you let q be other things... oh yeah, Raymond's going to tell us all about it in chat then. I mean, if you let q be other things, then we consider this a deformation of the affine Hecke algebra. That's my understanding, but Raymond's about to lay it on us in chat here. We're about to take us to school here about Hecke algebras. Yeah. Okay, do we go back and try and understand QCO again? Or what? The typical Hecke algebra is a deformation of the symmetric group algebra. Yeah. Yeah. That's the, I mean, type AN affine Hecke algebras, right? But you can generalize to other Weil groups. Yes. Yes. Yeah. Okay. We're getting close to the end. Oh. I feel how mad my spine is at me for doing this. I should actually probably go to the university gym so I can hang from something and let my back stretch out. Especially, I gotta sit on a plane only for like 2 hours tomorrow, but you can do it with any Coxeter system. I guess I could believe it. Right. I mean, I guess we've been here before. Am I really gonna understand this any better now? I guess we vaguely get the point, right? It's we take limits over quasi-coherent sheaves. Yeah, I mean, what else is there to say about this right now? 8 hours is a long time. Didn't even get that much sleep last night. Neither did I. Am I winning, son? Nope. I am not. I'm not Leo. Yeah. Joined us again for the home stretch. Yeah. Damn, this is a long book. This is a big book. How the hell did they even write all this? I can't even read it all. Complete amateur here about math. Question on category theory and ZFC. Shouldn't your functor just be a class function? Oh man, you're cooking up the debate from this morning. I think you can be able to define them properly true. Properly too. Yeah, I mean, technically a functor, if you want to formalize it, a functor is, yeah, I mean, one way to formalize it is a function from between two classes. Well, it could be sets. By the way, yeah, no one's responded to this post. I'm tempted to bring up the debate once more again through the analogy of the axiom of infinity, but perhaps we should leave that for like tomorrow morning. Yeah. Fight night 2, maybe. Yeah. How many we got? 18, the lowest since we started. Yeah, we're dragging here. We're really reaching for things in the last 30 minutes. Reaching for donations, hopefully, for the for the charity fundraiser that this is supposed to be. We raised a little money. Shall we go back to the book that started it all? Let's go back and do some basic exercises now that we've seen all this fancy stuff. Let's go back and do something really basic. Actually, I am hungry. I don't think I can go for a walk right away. I'm gonna have to eat as soon as we're done. I'm suddenly getting hungry. Oh, didn't mean to jump there. Infinity categories. Yeah, I don't even know what to. I don't know what to read at this point. I think this exercise, right? Probably there's something in this exercise we should be doing. You still say react to something? I'm reacting to the entirety of infinity category. Yeah, what I think, well, we have the archive paper recent publication, right? If I just Google this, maybe it'll come up again. Stated skeins and Dahas, this is the one, right? Watch the goats documentary. Which one? This is the paper. This is the paper here. Oh, the second one's your dissertation. I guess this is the preprint. The dissertation's probably got a little more juice in it. Wait, this one? Oh yeah, this is I see. Goat scurry. Daha is double affine Hecke algebra. Yeah. Yeah. Okay. Maybe we should try to learn something about limits of infinity categories in these final things here. Yeah. Terminal initial objects, if it's contractible, right? So let's go back to contractible. That's something probably from a while ago that we should have learned. So let's go. Okay. At a later stage of the book, we'll see that informally, an infinity category is a composer with a choice of composition that is unique up to contractible space of choices. Okay. So we haven't really defined contractible yet, but we will. Let C be a category with initial or terminal object. Then the nerve is contractible. Wait, what does it mean for the nerve to be contractible? I.e., its identity map is homotopic to the constant map at the terminal or initial object. Okay. So right, because this is in a simplicial set. Well, hang on. But what does that mean? So the nerve is a category. The nerve here is a category. It's a simplicial set. And we do have a notion of homotopic maps. Its identity map. The identity map. Yeah, but what's our notion of homotopy here? I'll have to go back up a bit. What if we reacted to the part of the stream where we fought and did a director's commentary? Yeah, that could be fun. That could be fun. Should have swept the leg and gone for a liver punch. Yeah. Yeah. Where are we here? Yeah, I mean, a homotopy. If X is a simplicial set, right, the homotopy is something between two one simplices. Right? The homotopy is between two one simplices. So what does it mean to say? Okay, if it's I probably should have just guessed that. Okay, simplicial set is contractible if its geometric realization is contractible. Well, sure. That to me is a believable and sensible thing. But then, how do I make sense of what this person was saying? Its identity map is homotopic to the constant map at the initial or terminal object. Maybe the proof is enlightening. Okay, whatever. I'll just take Jacko. I'll just take your definition because it makes sense to me. Now where are we? We're trying to learn about limits. Okay. But what about the mapping space? So that's another thing we haven't learned. If the mapping space is contractible. But this is an infinity category. So, well, okay, mapping space. Mapping space is the next one. Maybe like a long chain of morphisms? I don't know. Consider a simplicial category with CW complexes as objects and Hom simplicial sets given by a singular set of mapping space. But wait, you haven't defined mapping space. What is going on here? And then all of a sudden we're talking about mapping space on page 130. Okay. What is a mapping space? Collection of all topological functions. Yeah. We can give it compact open. but mapping space of, oh my God, too many group chats. Gonna mute that. Gonna mute this other one. Actually, I better mute this other one just in case. I will tell them you all say hi. Yeah. But I want mapping space of objects in a Simplicial set. I don't know. Damn, you miss math, Quen. You're doing software engineering now, and my God, do you miss pure math? You don't know how to get back to math. You have so many things to worry about that you don't have free time. Maybe we could trade lives for a while. You could come do the math I'm doing, and I could come make money in your software engineering job. Yeah. Maybe that. I don't know. Yanisium, you're a bachelor student in the second year of applied math in some random weak university. Any advice on how to get both the motivation and discipline to study mathematics? Well, motivation, no, because I've always liked mathematics. So, for motivation, I mean, I don't know. Either you want to study it or you don't. And if you don't want to study it, then don't study it. If you want to study it, then study it. Now, on the other hand, there is the matter of discipline, which I would consider slightly different. And that, I don't know. It just starts with, sometimes I'm bad at that, but it starts with small daily habits. Small daily habits, making promises to yourself that you'll, I don't know, turn off social media or whatever for a certain amount of time and sit down and study for a certain amount of time. Yeah, I don't know. But personally, I've just always had a desire to, you gotta have something worse going on, so doing math is distracting. Yeah. Have you tried making your life worse? Have you tried making your life worse so you can use it as a distraction? I mean, maybe Quen, that's the answer. That's the answer for you, is just start slacking off on your software engineering job, and working on math instead, until you get fired. No, don't do that. Any book in homological algebra seems to get to a point where the author just gets tired. Yeah, I feel him. Your topology prof said the same thing. Either you do it or you don't, and it motivated the hell out of you. Yeah, good. You do have the desire, but sadly you don't know what you want to do. I mean, that's fair. You're second year undergrad, so you can't even be, I don't think it's reasonable to expect that you really have a true understanding of what, the possibilities are. So, use some of your free time to explore other areas, and then, just keep grinding. Yeah, everything in life is about habits, And I've fallen off a bit on some of my habits lately, to be honest, but I'm getting my way back to it because I have built up so many good habits along my in my life that I start to just get used to it. So yeah, your life is so boring right now that mathematics is one of the few things that add spice. That's the other thing you do. Instead of ruining your life, you could always just try to make your life boring, as so boring that math is an attractive option. Yeah. Yeah, exactly. Exactly what Leo said. We define. Here we go. Here's a definition. Thank the Lord Girdle, our Lord Girdle above us. Let C be an infinity category, and let X and Y be objects of C. We define the right mapping space. Actually, hang on a second. What does it mean? What does it mean? What does it mean to be an object of an infinity category? In this book, an infinity category. Are we? Maybe this is an infinity 1 category. Okay, maybe this is an infinity 1 category. The right mapping space is defined by the pullback by this pullback. Okay. So it's a pullback. We're claiming these pullbacks exist. Forgetting from the slice category and delta 0 picking out X. And that's what the right mapping space is. If you don't sleep well, why? I have a lot of theories, and they don't all seem to be panning out. Is it some social thing keeping up late? No. Is it watching stuff? Sometimes. Make active changes to change. Well, that's what I'm doing. Finding definitions in this book is like an oasis in the desert. An object is an element of C naught, which is equivalently a map from delta 1 to C. Yeah. Well, but this depends on what's an infinity, because what do we mean by infinity? Infinity 0 or infinity 1? Because I mean infinity 0. Wait. Right. Okay. It's the same thing as delta naught into C. It's the same thing as delta naught into C. Because by an infinity category here, we mean a simplicial set satisfying the inner horn filling property. Okay. So this is how we define mapping spaces. Okay. And they're both vibrations, whatever the hell those mean. Home stretch, yeah, last 15 minutes. Oh. You best believe I'm going to get the hell out of here. What am I going to do? I'm going to eat, and then maybe I'll go to the gym. I don't know. I should probably go to the gym and just even walk on the treadmill for a while. Infinity 1 category equals infinity category equals inner con complex equals quantity category. Okay. Can we learn a DAW is in 15 minutes? We might be able to. Wow. Anonymous. Coming in clutch in the home stretch. $75. Suddenly jumping ahead. I think the previous we were tied at 3 people at $20. Blowing ahead, blowing away the competition. Anonymous. $75 to Children's Hospital and Research Center. Damn near. I mean, that's like a 50% increase from what our previous things were. Damn, Anonymous. Thank you for coming in clutch right at the end here. That's fantastic. Yeah, now we've made and with this we've definitely justified. We've now raised more money for the kids than if we had been working a minimum wage job today. So now quite a bit more. So that's the goal, I guess. Can we watch the first half of Leo Lecture's video? Not today, maybe tomorrow. Yeah, go watch Leo Lectures after this, because obviously 8 hours of streaming isn't enough for you animals. Okay. And then the following, okay, so what is it? So we defined left and right. Hang on. Something fishy is going on. We defined left and right mapping spaces. I'm happy with that. We define these things called pullback. Okay. And what do you mean the following diagrams are pullbacks? What do you mean? We can then use the following lemma to compare the various definitions of mapping spaces. We can? What does this lemma have to do with mapping fibration? Oh my god. No, where's even the whatever? Okay, whatever. I'm gonna ignore it, and we're gonna go back to the section on limits. Oh, holy crap! I wasn't paying attention. We got another. Another donation. $100. MX. Actually, I don't know. I don't know the conversion rate, but no. But in any case, thank you so much. Coming in, people are coming in the last minutes here to really boost us across and up our goals. So thank you so much. By the way, this video will still I'm gonna leave the fundraiser on the video like indefinitely, so I think people can still donate via this video. $550 USD. Well, it's still appreciated. Every small amount is appreciated. Can I recommend some intro book / notes for representation theory? You watched my new video. You don't think I mentioned something there? I've not read it in detail, but I was teaching some students some representation theory this semester, and one of them came across Steinberg's book. And actually it looked pretty good. I mean, there's other ones. There's like Invitation to Representation Theory by Howe. There's Sayre's book. Maybe it's not the best for a first pass, but I would maybe go look at Steinberg actually. From what little I've seen of it, it seems pretty good. Some say he is still looking for definitions to this day. Yeah. Yeah. Okay. So whatever. Okay, whatever. A mapping space, I guess. The mapping space itself should be a simplicial set. And if we're saying that it's contractible, we're saying that the nerve of that, the geometric realization of the nerve, is contractible. I guess. Okay. Then the following conditions are equivalent. This is a trivial fibration. For every n equals 1, the lifting problem admits a solution. Okay. So, let this be a full subcategory spanned by all terminal objects. What? If they exist, they're unique up to contractible choices. Wait. Oh, an object is said to be initial if for all objects the mapping space is contractible. I see. Right. And then we prove that terminal and initial are unique. Okay. Actually, well, the category, the full subcategory is either empty or a contractible complex. I see. So it could not exist. Right. But if it does, then it's a contractible complex. A definitions only book, basically a math dictionary. The only problem is you kind of need to have things like you for some definitions you need proofs, right? You need to prove that something is true in order to make a definition valid or something, right? Yeah. Object is initial, if and only this. Yeah, we didn't even get into anodyne maps. Oh well. Supposed to be given a functor. Let C be an infinity category, K a simplicial set. And supposed to be given a functor from K into C such that for all objects, the object is initial. Oh, then F is initial in the functor category? Such that all objects are initial? That seems like a crazy thing, though. Maybe I need proofs. Yeah. 218 over 8 hours, 27.25 per hour. Not bad. Not bad. Yeah, not bad indeed. Not bad indeed. So, yeah. Good job, gang. Good job. Suppose that this is not empty. Then the terminal object of this takes values in here. Okay, wait a second. That's it? How does this... Well, okay, I guess there's more sections here. Wait, 4.2. That was terminal initial. Okay, 4.3. Right, we wanted to go to 4.3. So now, in the last couple of minutes here, that's a restaurant manager teacher salary. All you need to do is rob them kids. Well, thankfully, that would be pretty difficult to do. In this section, okay, well, definition, colimits of diagrams, phrased in terms of if they exist or unique, and show that all infinity categories admit these things. Afterwards, we'll use these to indicate how one can show that these If you're somewhat familiar with abstract algebra, you would argue Artin's Algebraic contains a super gentle introduction to representation theory. Oh. This is Marcus Land's book. On infinity categories. Let's see how many people are here for the last couple minutes of stream. We're not up to 22 again. Let's see, did we get any response to my thing? No. Maybe it's a stupid question. Okay. For all objects, okay. F is a functor. L is a map of simplicial sets. Then for all objects C, I induces a map on these spaces. If I is right anodyne, then it's a homotopy equivalence. I don't know Erdmann and Helm. I'll have to check that out. For the proof, okay. Okay, so now we have a functor. Whoa, what is this thing here? This is some trivial product category. And a cone over F. We say that F bar is a colimit cone if all objects X of C, if for all objects F of C, the canonical map is a homotopy equivalence. Okay. It's written for undergrads with basic abstract algebra background. If you want to study rep theory, you should be familiar with abstract algebra already. Yeah. Could be nice to have it, an introduction in the back of the book where you've got all the other definitions, though, right? That is a star. It's the join of simplicial sets. I see. Well, I don't know what that is. You're reading TOC for Eerdman and looks pretty good for your background. Okay, nice. Yeah. Colimit cone. Yeah, I guess there's just other definitions I should have read. I've done this whole stream in the worst way possible, to be honest. What did I do? I spent like an hour arguing about set theoretic issues that I might be wrong about. And then I jumped ahead to things that are way too advanced. Yeah, what can I say? Well, 4 o'clock. We did it, gang. We did it. We raised a bunch of money for the kids. We maybe learned something about infinity categories. I don't know. But thanks for joining me anyways. I'm going to get the hell out of here and stretch my legs and stretch my spine. You all should too. QED.